Hello and welcome to Sleepy Science. I'm so glad you're here. What if tonight we let curiosity move at the speed of calm? What if a single photon could paint with two hands? A mirror could tip fate. An unseen object could reveal itself without a touch. Randomness could be proven honest. And distant labs could share a whisper without anything crossing the gap. Before we begin, where are you listening from and what time is it? Under quiet stars or in warm indoor light? If this gentle wander helps you rest, please like the video and tap subscribe. It helps more sleepy minds find their way here. Now take a slow breath, feel the bed hold you, and let's drift. Double-slit with single photons. You start in a room so dim, your eyes keep searching for shapes they can't quite find. And in that hush, you're asked to watch something that sounds almost too simple to be interesting. A stream of single photons, released one by one, toward a barrier with two narrow openings and a detection screen beyond. No floods of light. No dramatic beams, just solitary quanta-like soft footfalls on a long hallway, each leaving a tiny dot wherever it lands. And if everything you learned from everyday life applied here, you would expect the dots to pile up in two bright bands right behind the slits, the way thrown pebbles make two plumes in sand. Yet as minutes pass and the screen slowly sprouts points of light, a striped pattern begins to appear, bright then dim, then bright again across the whole field. A pattern you usually associate with overlapping ripples on water, not with single isolated impacts. And you feel your stomach tip a little because every photon hit the screen at only one place. But the total arrangement of those hits has the signature of waves combining. To make sure no hidden multiple at once trick is responsible, the source is turned down so low that the time between emissions is far longer than the travel time to the screen. Or a heralding method is used that tells you a partner photon was detected and its twin is on the way. Either way, you have strong reason to trust only one photon is in flight when each dot appears. Yet the pattern keeps building as if each photon somehow sampled both slits. In the language physicists use, you don't add up ordinary probabilities like coin tosses here. You add up the wave-like chances first. Let them strengthen or cancel each other depending on their relative peaks and troughs. And only at the end square that result to get the probability of where a hit can happen. Without equations, you can picture it like this. If two faint water waves meet crest to crest, the water rises higher. And if a crest meets a trough, the water flattens. And the screen records those outcomes one pinpoint at a time. But it's not enough merely to carve two slits. You also need the light to be coherent, meaning that the tiny ripples of each photon's wave keep a steady rhythm over the distance from the source to the barrier to the screen. If the rhythm wanders too quickly, the bright and dark bands blur and disappear, so experimentalists pick a wavelength and a slit spacing that let the ripples line up in stable ways at the screen. When those requirements are met, the slits clean and narrow, the separation comparable to the wavelength, the source coherent. You get an unmistakable fingerprint. The bright bands are where the two possible paths reinforce one another, and the dark gaps are where they cancel so completely that you almost never see a dot at all. Even after long patience. The oddity that makes you pause is that the pattern still forms when photons arrive alone. A single photon never lands in pieces. Yet the distribution of many solitary landings betrays an underlying wave rule in how the possibility for each landing spreads out and overlaps through both openings before the screen forces a single, definite result. If you ask where the photon really was between source and screen, you'll find different interpretations of quantum theory tell different stories. Some say it doesn't make sense to ask. Others say the photon traveled like a wave until detection. Others try to keep a particle picture with extra hidden variables. But the remarkable thing is that they all agree on the measurable pattern when the setup is the same. It's tempting to think the interference means your knowledge or your gaze is somehow rearranging the world. What actually matters here is not a human looking with eyes, but whether the experimental arrangement preserves the necessary coherence and whether there is any mark, even in principle, that could reveal which slit the photon took. Keep that principle in your pocket for later, but here, in the simplest version, nothing in the apparatus tags the path, and the interference is free to appear. If you want to test your intuition, change the geometry. Move the slits slightly farther apart and notice the bright bands squeeze closer together. Use shorter wavelength light and the bands widen. Open and close one slit and watch the pattern switch between two-lobed particle-like spread and many-lobed wave-like fringes. Place the screen nearer or farther and see the spacing change because the paths from each slit meet at different angles. All these variations match a simple wave picture that's been verified again and again with cameras, photomultiplier tubes, and time-tagging electronics that record each arrival. The experiment also teaches you to respect scale. Macroscopic objects don't show the same fringe clarity because their associated wavelengths are ridiculously tiny and their surroundings constantly disturb their delicate rhythms. So the coherent ripples needed for crisp interference are washed out long before they reach any screen. Photons, electrons, even large molecules under carefully controlled conditions can keep those rhythms long enough for their own interference to appear. But your tennis ball won't cooperate. If you let the room fall quiet enough, a different kind of realization settles in. The either-or instinct you rely on in daily life is a brilliant shortcut within a narrow range of experiences. Yet nature's deeper bookkeeping allows both paths to influence outcomes. And only at the final moment of detection do you get the single dot your instincts expect. It isn't that the world is playing a prank on you, it's that your habits were trained by objects that constantly leak information to their surroundings, and so hardly ever display the subtle wave rules that single quanta obey. There's a sober lesson here for how you think, not just how you measure, before you decide what must be true based on the categories that work in ordinary rooms. Ask whether the situation preserves the quiet conditions under which multiple possibilities can still speak to one another. If it does, expect patterns that reflect combination rather than simple addition. And if it doesn't, expect the familiar spread that looks like particles flying through one opening or the other. And as the last few points appear on the screen and the bright and dark stripes become undeniable, you're left with a strangely calming thought. The universe is consistent even when it feels counterintuitive. And if you are patient enough to let the evidence accumulate, the shape of truth often arrives one dot at a time, slow, precise, and exactly as it must be. Mirrors that decide fates. You don't expect a tiny turn of your wrist to decide the fate of a single particle of light. Yet when you rest your fingers on a mirror mount and nudge it by less than the thickness of a hair, the detector that was clicking with confident regularity goes silent while its twin across the table wakes up. And you realize that in this quiet experiment, polished glass is not just reflecting, it's choosing. Not because mirrors think, but because their angles and distances set the rules that a lone photon must follow from launch to the final click. And your small adjustment has just rewritten those rules. To see how this choice works without resorting to dense math, picture a simple interferometer built like a tiny city of glinting right angles. A beam splitter at the entrance that sends each incoming photon into two possible routes. Two high-quality mirrors that fold those routes around like elbows in a maze. And a final element that either brings the routes back together or keeps them apart. When you allow the two routes to reunite, something surprising yet repeatable happens. One output port brightens while the other goes dark, even when you send photons one at a time. Not bright and dark in the way a flashlight overwhelms a room, but bright and dark in the sense of long-term statistics. Hundreds, then thousands of clicks piling up at one detector, barely any at the other, as though the entire device were steering the photon to a preferred exit. The steering knob is the phase, the tiny timing difference between the two routes. And your mirrors control that knob with exquisite sensitivity. Slide a mirror forward by a fraction of the wavelength, and you shift when the peaks and valleys of the light's rhythm arrive at the recombining element, flipping which detector does the talking. For this to work, the optical surfaces have to be extraordinarily stable. The mirrors carry multi-layer coatings that reflect almost everything while introducing a controlled delay. Their mounts sit on isolation platforms to quiet the tremor of footsteps, and piezoelectric stacks move them by nanometers so that the fragile rhythm remains intact. If the laboratory air stirs too much or the table hums, the contrast between bright and dark collapses because the two routes no longer arrive in lockstep. Now, change just one detail at the end of the maze. Remove the recombining element that mixes the two routes, and you get a very different story. Each detector now acts like a path tag, lighting up for the route that points its mirror toward it. With the routes no longer combined, the device will not prefer one exit over the other, and your counts split nearly evenly. You can put this switch on a timescale faster than a blink by using an electro-optic device that can act like a mirror or disappear on command. Flip it in the last microseconds, and the statistics align with whatever setting you chose at that moment. Some people hear this and think backwards in time influence, But that's not required. Nothing in the records shows a contradiction with ordinary causality. What matters is the total arrangement the photon encounters on its way out, and the photon's fate is simply the outcome predicted by that arrangement. If the roots are kept separate and could, even in principle, leave a trace of which direction the photon took, you observe a fair split. If the roots are brought together so perfectly that they become indistinguishable pathways of a single outward story, you observe a strong preference for one exit over the other. That preference is fragile in all the ways practicality teaches you. Imperfect mirrors leak a little light, dust softens edges, thermal drifts swell the metal subtly, and each of these erodes the clarity with which the two roots can be treated as one. Experimentalists watch this erosion happen in real time by plotting the ratio between maximum and minimum counts. When the ratio is high, their mirrors are doing their job as fate setters. When it slumps, they hunt down the source of noise, tighten bolts, dry the air, and nudge the phase back into place. To keep the story grounded, it helps to know what's inside those gleaming mounts. Dielectric stacks, alternating layers so thin they make human hair look like a mountain. Tuned to reflect with minimal absorption, the stacks add a tiny, predictable delay on each bounce, and that delay, combined with the exact geometry of the paths, sets the phase. The second mirror does the same on its arm, and the final element recombines those two carefully delayed contributions. In the single photon regime, you won't see a dim glow. You'll hear ticks from avalanche photodiodes or watch time-stamped dots accumulate in software, and that makes the device feel almost like a voting machine in which the ballots are set by mirror angles. Turn the phase dial one way, and the left detector wins almost every time. Turn it the other and the right detector wins. Sit in between and both collect similar totals like a tie. Here's a check you can run without fancy math. Keep the recombiner in place and slowly tilt one mirror. You'll see the totals swing back and forth between the two detectors in a smooth rhythm. Stop where one is nearly silent and you know you've aligned the roots so that the device funnels the photon to its partner. In practice, labs lock to that sweet spot by feeding back the detector counts to the mirror's piezo and letting a controller keep it there for hours. You can raise the stakes by making your end choice unpredictable. Drive that electro-optic switch with a high-speed random number generator that decides whether the recombining element is inserted or not after the photon is already winding its way through the maze. The logs still separate cleanly into two sets, one with strong steering, one with equal splitting, matching the configuration at the output. There's no need to suppose the photon knew in advance or was influenced from the future, only that its final statistics are set by whether the device reunites or separates the roots before detection. None of this demands that mirrors have minds. It demands that you respect how boundaries shape possibilities. The polished faces define where light can go and how two histories can be made indistinguishable enough to merge into a single exit, or kept distinct enough to be sorted into two. In that sense, deciding fates is what any well-designed boundary does. It sets a landscape where different outcomes become more or less likely. The practical lesson is as down to earth as a wrench and as deep as your patience. Small, deliberate changes in alignment reshape what outcomes are available, not by force but by permission. When the roots are allowed to speak together, a lone photon almost always leaves by a chosen door. When they are kept apart, it behaves like two separate stories, each ending at its matching detector. And there's a human lesson hiding in the hum of the optics table. We often treat choices like mirrors as decorative, mere reflections of what's already certain. Yet in careful systems, the choice of boundary is the system. Outcomes are not fixed objects waiting to be uncovered, but patterns that emerge from the way paths are combined or kept apart. In the lab, your fingertips on a mirror mount decide which pattern survives. And in your thinking, the frames you allow to meet or forbid from meeting decide which explanations grow bright and which fade into the quiet. Photons that refuse to pass. You point a small, steady red dot at what looks like a clear chip and expect a bright spot on the other side. Yet as you tilt the sample a little, the output vanishes as if the material flashed a tiny no entry sign at your photon. And that simple moment opens a door into how light can be stopped not by brute force, but by design. What makes a photon refuse to pass is rarely magic or myth. It's structure, rhythm, timing, and when those align just right, Even something that seems transparent can turn into a gatekeeper, reflecting or absorbing a very specific color angle or polarization with the calm authority of a turnstile that knows when to lock. Start with periodic structure, the gentlest kind of order you can build into matter. Layers so thin they make a strand of hair look thick, or a checkerboard of holes etched into glass at scales smaller than the wavelength. When the spacing is just right, the multiple tiny reflections from each layer or row add up in a way that cancels forward progress and piles energy up going back, creating a stop band where transmission plummets. This is the essence of a photonic crystal, and it's why certain butterfly wings and peacock feathers glow with vivid blues and greens without any dye. Their microscopic patterns select which wavelengths may pass and which must bounce, so the color you see is structure made visible. Engineers turn that same idea into tools. A fiber Bragg grating, an invisible periodic ripple written inside optical fiber, reflects one narrow band of telecom light while letting neighboring colors through, acting like a mirror that only cares about a single note. Multi-layer Bragg mirrors do the same on chips and lenses, and by flipping the recipe, you can make either a nearly perfect reflector that says no to a chosen band, or an anti-reflection stack that says yes and quietly steps aside. Sometimes the refusal isn't reflection but a perfect, almost theatrical disappearance called coherent perfect absorption. Nicknamed an anti-laser, you feed light from two sides into a slightly lossy film or cavity with exactly adjusted timing, and the outgoing beams cancel. The energy doesn't escape because it's soaked up by the material, turning into heat or an electrical signal, and the outside world sees nothing. This is not trick photography. It's the everyday interplay of interference and loss tuned so precisely that transmission and reflection both drop to zero, a switch you can use for modulators and sensors that need robust on-off contrast. Even basic geometry can enforce a pass or stop verdict. Tip a beam inside glass beyond a certain angle, and total internal reflection slams the door. The wave can't push power into the air, so it fades along the boundary as an evanescent whisper that dies in a fraction of a hair's width. Press a second glass block within that. Whispers reach and the refusal softens. The wave can jump the gap in a process called frustrated total internal reflection, reminding you that a barrier can be absolute or porous depending on how closely you shadow it. In the world of devices that must be protected from their own echoes, a different kind of refusal shows up. Non-reciprocal components like Faraday isolators let light leave a laser but block it from returning, the optical equivalent of a one-way door. A crystal under magnetic bias rotates the polarization just enough that, after reflections and a return trip, a polarizer rejects the backward beam. Nothing in the material has a will, but the asymmetry you designed into the path creates a direction with privilege and one without. Push down to the scale where single quantum matter and you meet refusals born of interaction, not just pattern, inside a tiny optical cavity strongly coupled to a single atom, quantum dot or superconducting circuit. A phenomenon called photon blockade can occur. One photon in the cavity changes the conditions just enough that a second photon of the same color no longer fits the resonance. Like a subway turnstile that permits one person but locks for the next until the first has moved on. The result is anti-bunched light, a stream with gaps that advertises how strongly light and matter are talking to each other. And that refusal is so crisp, it becomes a resource for building single photon sources and gates that need strict, one-at-a-time behavior. Materials can also become choosy with intensity. Some pigments and films absorb more the brighter you shine, and therefore clamp down on sudden spikes. Others do the opposite and become transparent at high power, a principle that underlies ultra-fast lasers. In both cases, the decision to block or pass depends on how hard you push, giving you a natural brake or throttle for light. In more exotic architectures, entire chips direct photons to coast along edges while forbidding them from wandering through the interior. Topological photonics, so defects that would normally scatter light barely matter because the edge states are protected by the way the lattice is patterned. Again, the chip hasn't learned a rule, it simply embodies one, and the photon obeys because the only low-loss highway the pattern allows hugs the boundary. If you want to feel these ideas rather than just hear them, pay attention to how narrowband mirrors for cameras sparkle with a specific color and go dark for others, or how an anti-glare coating makes the world look more true by refusing to reflect. Look at dragonfly wings whose transparent panes hide a subtle grid that decides which glare never reaches your eye. Notice that the slender glass thread that carries the internet has mirrors written inside it that bounce unwanted channels away. See that the little black block strapped to a laser is a one-way gate that keeps the instrument calm. Understand that deep inside a cryogenic cavity, one particle of light can be persuasive enough to turn others back until it leaves. The pattern tying these scenes together is not superstition, but selectivity. Whenever a system sets up a stable rhythm, a periodic lattice, a resonant chamber, a polarization rule, a protected path, it grants passage to light that fits the rhythm and quietly refuses what does not. Sometimes the refusal sends the photon back the way it came. Sometimes it absorbs it. Sometimes it delays it until it can be released in a different direction or at a different time. But in each case, the outcome is predictable and useful. Once you know the rule, the structure enforces. And if there's a human-sized lesson to carry from the lab to your life, it's this. Boundaries are not only walls, they are filters. The right kind of order makes clarity by saying no in very specific ways. And in that refusal, whether in glass, in circuits, or in your schedule, there is the freedom to guide what truly matters through while the noise stays politely outside. Interaction-free imaging of fragile samples. You're told there's a way to learn about something so delicate that even a whisper of light could harm it, and your first reaction is doubt. How can you make an image without letting photons actually strike the thing you're imaging? Yet that's the promise of interaction-free imaging, arranging the experiment so that a yes, it's there signal appears precisely when a photon has not touched the fragile sample at all, and then using many such signals to build a picture with almost no dose. The heart of the trick is a carefully staged either-or that collapses into a telltale click. You prepare a single photon so it has two possible stories, one that would pass through the region containing the sample and one that would avoid it, and you tune the apparatus so that, when no sample is present, the two stories cancel at one detector and reinforce at another, sending practically every photon to a bright exit and leaving the dark exit silent. But if an opaque sample is present in the danger zone, the sample blocks just one of the stories and ruins the cancellation. And suddenly the dark exit begins to click, even though the photon that caused that click traveled the safe route. That one dark click is a small, logical miracle. It tells you the sample existed in the dangerous path without paying the usual price of an absorption event. In the foundational version, sometimes nicknamed the bomb tester, this logic simply detects presence. But imaging asks for more than a yes, no. It asks for a map. So you repeat the test across many tiny regions, either by scanning a beam across the sample or by forming many danger zones in parallel with a camera. Where you get dark port counts, there is something that would have blocked. Where you get the usual bright port counts, there is likely nothing. Stitch those statistics together and the outline appears. A silhouette drawn with almost no light delivered to the subject. The method becomes dramatically more efficient when you wrap it inside a quantum Zeno-style loop that lets the apparatus ask the same question many times without ever forcing a harmful interaction. You send the photon into a cavity or a cycling circuit that would, in the absence of a sample, gradually steer it toward the bright exit after many gentle steps. But if a blocker is present in the risky branch, its mere possibility of absorbing freezes that steering. After enough cycles, the photon leaves instead by a special "there's a sample" exit, still unabsorbed. This upgrade can, in theory, push the probability of success very close to unity while keeping the chance of actually hitting the sample extremely small. In the lab, that loop isn't magic, it's hardware. Ultra-reflective mirrors, or waveguides that let a photon bounce thousands of times. Polarization rotators that turn the photon's direction in tiny increments, and fast detectors that register which exit fired. The sample is placed where only one of the photon's options would expose it, and alignment is tuned so strictly that the system only produces dark port clicks when the sample's presence has broken the delicate balance. Because you care about truth rather than drama, you should know the limits. The process is not perfectly zero interaction. There remains a small chance that a photon will be absorbed, especially if the sample isn't fully opaque, and technical noise can smear the logic and cause false positives or missed detections. Also, the basic setup detects opacity, not subtle phase shifts. So transparent but phase-shifting structures need specialized extensions that convert phase changes into the kind of cancellation break the dark port can read. Finally, building a full image is slower than blasting the scene with bright light, because each pixel's verdict comes from many single-photon trials. Still, the advantages for fragile targets are real and measurable. Imagine an organic dye that bleaches with a handful of absorbed photons, a protein that changes shape under illumination, an archived document whose inks are photosensitive, or a prototype photonic device you don't dare flood with power. Interaction-free strategies let you probe where is stuff, while spending most of your photon budget on inference rather than exposure. To keep terms straight, this is not ghost imaging, which uses correlations between two beams to reconstruct a picture. Here, the image is counterfactual in a precise sense. You infer that if a photon had taken the dangerous path, it would have been absorbed, yet the detected photon demonstrably did not, and its safe arrival at the dark exit is the very evidence that the dangerous path was blocked. Practically, you implement it as a microscope add-on, an input that prepares single or heralded photons, a cycling section that performs many gentle asks, a sample plane where only one option would poke the subject, and a sensor array at the outputs to collect the statistics. You calibrate the device with known patterns to map dark port rates into pixel values. You control temperature and vibration to keep the balance sharp. And you choose wavelengths that the sample would absorb strongly, so the logic signal is crisp even with few trials. The most satisfying part is how the method shifts your intuition about measurement. You grew up assuming learning always requires touching, that information and disturbance are welded together. Quantum interrogation shows a more subtle bargain. If the rules are arranged so that a certain outcome requires two possibilities to be indistinguishable, then anything that would make them distinguishable, even the mere threat of absorption, leaves a footprint in the statistics you collect elsewhere. You discover by creating a world in which nothing happened here is itself a message, and that is the ethical, almost tender promise of the technique. You respect the thing you are studying by designing a question it can answer without being harmed. You accept slower progress and careful alignment in exchange for truth carried in the quiet clicks of a dark output. And you leave with an image that is as much about what did not occur as about what did. A silhouette written by the absence of interaction. Proof that sometimes the most responsible way to see is to ask the world to tell you, in its own unbroken voice, where it would have said no. Weak value amplification for tiny effects. You don't normally expect a needle to jump when the thing you're measuring barely exists, yet in a quiet optics lab, you can turn a knob by less than a degree and watch a camera spot lurch as if the world just shouted. That is the strange promise of weak value amplification, a way to make tiny effects visible, not by blasting a system with power, but by arranging preparation and filtering so cleverly that the leftover light carries an exaggerated version of the change you care about, a kind of stethoscope for whispers that would otherwise drown in the hum of your setup. The recipe sounds simple when you say it plainly. First, you prepare your photons in a known internal state. Polarization is a favorite, but it could be a path in an interferometer or a spin in a solid. Then you let them brush past the effect you want to sense with the gentlest possible touch. A weak interaction that links that internal state to a meter you can read, like a minuscule position shift of the beam, a tiny timing delay or a slight color tilt. Finally, you filter the photons with a nearly orthogonal analyzer, so only a rare subset makes it to your detector. In ordinary thinking, this sounds like sabotage. You're throwing away most of your light. Yet here's the twist. The survivor's average meter reading can be pushed far from the tiny, barely noticeable kick you applied, sometimes even outside the range you'd think possible, because the post-selection forces two almost cancelling contributions to combine in a way that leaves a large residue where the meter lives. Said without equations, you create two overlapping populations of photons that nudge the meter in nearly opposite ways. Then you tilt your filter so it almost erases one population, and the remaining sliver shows a big net shift, even though each individual nudge was small. The amplification is real in the sense that your camera centroid or your photodiode balance genuinely moves by an amount you can calibrate, but it isn't magic. You paid for that big step by keeping only a small fraction of the original photons, so the total information you harvest can be similar to more straightforward methods. What weak value amplification buys you is not a free lunch in precision, but a different menu for fighting the kinds of noise that actually plague your table. If your detector saturates at modest power, post-selecting a small stream of photons while making their average shift huge can move the signal into a clean, linear regime. If your electronics suffer from slow drifts and 1F noise that swamp tiny deflections, stretching a subpixel motion into a multipixel slide lets you resolve it above that technical rumble. If beam jitter or power fluctuations dominate, shaping the output so that the signal rides on a levered pointer rather than on total intensity can make the measurement robust against those nuisances. But if you are limited only by the fundamental counting noise of photons, the advantage largely evaporates, and a conventional balanced measurement often matches or beats it. The hardware looks approachable. A polarizer to define the starting state, a weak coupler like a thin birefringent crystal or a very slight mirror, tilt in a Sagnac, or Mach-Zehnder loop that ties polarization or path to a transverse shift, and an analyzer set almost, but not quite, at the state that would normally block everything. By turning the analyzer toward that near-dark angle, you set the gain of the effect and also the scarcity of surviving photons, and you find a sweet spot where the amplified pointer clears your noise floor without starving the detector. Early demonstrations use this to see displacements so small they live well below a pixel's width, beam deflections from a minuscule mirror rotation, timing lags that would hide inside a single camera exposure, and delicate polarization-dependent shifts at a glass boundary that had been predicted but were hard to catch directly. Later versions moved beyond free space beams to integrated waveguides and even solid-state qubits, where the same pre-weak post choreography can boost tiny frequency changes or phase drifts into something electronics can grab. To keep yourself honest, you calibrate the amplification by deliberately injecting a known tiny tilt or phase and verifying that the post-selected output multiplies it by the expected factor. You track how often a photon survives the filter to make sure you're not fooling yourself by rare lucky counts. You monitor common mode fluctuations to confirm that the method is indeed rejecting the noise channel you designed it to fight. There are boundaries you can't wish away. If the effect you're chasing varies from shot to shot, the filtering can bias which instances you keep and which you throw, so you must model that selection. If the sample adds loss or extra wander, the carefully balanced near cancellation that makes the meter swing can smear out, shrinking your gain. And if you push the filter too close to perfect darkness, you'll wait too long for usable data and drift will undo your advantage. A practical mental model helps. Imagine two choirs singing almost the same note, one slightly sharp, one slightly flat. From far away you hear a bland average. Now you put on a headset that suppresses almost all of the flat choir and lets a sliver through. Suddenly, the tiny sharpness becomes glaringly obvious in what you hear, not because the singers changed pitch, but because your filtering turned a subtle difference into a big audible offset. The price is that you're hearing fewer voices, so you must listen a bit longer or accept a grainier sound. But if the room's air conditioner is roaring, the headset still wins. In metrology terms, that's the niche where weak value amplification earns its keep. When you have headroom to throw away power, when technical limitations, not nature's fundamental randomness, set your floor, and when what you need most is to reposition the signal into a cleaner part of your instrument's dynamic range. There's also a conceptual lesson tucked inside the optics. You're not amplifying energy or breaking any rules. You're amplifying meaning by conditioning on a rare outcome that sharpens a tiny difference. A reminder that sometimes the most efficient route to clarity is to keep only the frames that carry the contrast you need and let the rest pass by. Used carelessly, that becomes cherry picking. But used with calibration and a clear model, it's a disciplined way to make the almost imperceptible readable in real time. And when you finally watch the enlarged spot breathing slowly across your screen as you brush a mirror by an amount smaller than dust, you feel a quiet shift in your own habits. Progress doesn't always come from pushing harder. It often comes from arranging the question so the answer stands where you can actually see it. Trading brute force for thoughtful preparation, a soft touch, and the courage to listen only to what truly carries the story. Super resolution via quantum light. You're taught that resolution hits a wall when features get smaller than about half the wavelength of light, a blur limit that feels like physics laying down non-negotiable terms. Yet the moment you stop trying to overpower the blur and instead change the kind of light you use, the wall starts to behave less like stone and more like a gate with hidden keys. Super resolution via quantum light doesn't shrink the wavelength in the usual sense. It reshapes how information rides on photons, through correlations, entanglement, and engineered noise, so that details normally washed into a single fuzzy spot can be teased apart without pretending the basic optics are wrong. Begin with the reason the wall exists. Lenses turn point objects into little ripple patterns, so two nearby points merge unless their patterns are sufficiently distinct. That is the spirit of Abbe's limit, and with ordinary, uncorrelated light, you pay a fixed price in blur, determined by wavelength and aperture. But if you illuminate, collect, or process with non-classical states, the statistics at your detector can carry sharper signatures than the raw intensity would suggest. One route feels almost like sleight of hand, but is solidly physical. Prepare light so that multiple photons act as a single joint traveler, arriving in lockstep with a fixed relationship that makes their combined interference pattern oscillate faster than any one of them could produce alone. In the idealized version, an n-photon bundle produces fringes n times finer, so a two-photon pattern has half-size stripes, a direct path to sub-Rayleigh features for writing or reading fine structure in phase objects or lithographic films. This quantum lithography idea is beautiful but demanding in practice because those fragile joint states hate loss, and most materials don't readily perform clean n-photon absorption. So today you see small n demonstrations that prove the principle and inspire hybrid tricks rather than mass production chips that rely on them. A second route keeps both feet on the detector side and asks more from your measurements than from the light source. If your scene is made of single photon emitters, quantum dots, certain color centers in diamond, rare earth defects, each behaves like a strict one-at-a-time lamp, never delivering two photons simultaneously. By recording not only how much light hits each pixel, but also how those clicks are timed and correlated across pixels, you construct higher-order maps that sharpen the effective point spread function. Write it down as a rule of thumb. The second-order map is narrower than the raw image, the third-order narrower still, and so on, letting you separate two emitters tucked well inside what would normally be a single blur. This is not wishful processing, but a physical difference in photon statistics. Anti-bunching, that hands you extra separability if your detectors can time tag and count cleanly. A close cousin extends the idea to blinking or fluctuating sources. When emitters turn on and off independently, the tiny differences in their twinkling patterns ripple through the correlations of the detected signal, and careful analysis can pull apart contributors that optics alone would merge. You might think of it as letting random telegraph noise draw a hidden contour map that a patient algorithm can read. A third path attacks the limit, where it so often bites you in practice. Not in spatial blur itself, but in the noise that buries the high-frequency contrast you need to claim you've resolved anything at all. This is where squeezed light enters like a good audio engineer, quieting the hiss in the channel you care about so that weak structure stops drowning in shot noise. By injecting a squeezed vacuum into the dark port of a microscope or interferometric sensor, teams have shown contrast improvements at power levels that would otherwise be hopeless. And while squeezing does not change diffraction by fiat, it inches your practical resolution forward by boosting the confidence of small differences in a fixed exposure time. Exactly the trade you want when the sample punishes you for pumping more light. Another family of techniques uses correlations between paired photons born together in a nonlinear crystal to improve axial and depth resolution in interferometric ranging. When you measure coincidences rather than intensity, the interference pattern that defines your slice through the sample can sharpen and, remarkably, resist the smearing that ordinary dispersion would cause. This quantum-style OCT does not grant infinite clarity, but it cancels one of the most stubborn blurs in layered, watery specimens and has already pushed edge definition beyond what the same bandwidth would permit classically. Structured illumination also gets a quantum twist. Illuminate with patterns that your detector decodes with the help of entangled or correlated light, and you can shift normally inaccessible, high spatial frequency information into a band you can collect. Classical structured illumination microscopy already doubles resolution by clever mixing in Fourier space, and quantum correlations promise similar or better gains at lower doses or with improved robustness against noise, an enticing prospect for live or light-sensitive samples where every extra photon counts. None of this means the road is effortless. Entangled states that promise the most dramatic n-fold sharpening are famously allergic to loss, scattering, and imperfect mode matching. So most current successes live at small n in carefully prepared optical benches. Correlation-based super-resolution asks a lot from your hardware: fast single-photon detectors, clean timing electronics, rock-steady stages, and from your math, which must be honest about confidence intervals and avoid hallucinating detail where count rates are thin. Squeezing once quiet lasers and low-loss optics to preserve the noise reduction you fought to create. And in every case, you must calibrate with known targets to prove you've won real resolving power rather than prettier pictures. Yet the payoffs are tangible and growing. Quantum emitter mapping now pinpoints defects in semiconductors that would hide inside a diffraction spot. Correlation microscopy separates individual fluorophores in crowded biological labels without resorting to destructive power. Squeezed light enhancements reveal subtle refractive index variations in cells that were previously buried. Two-photon interference has been used to carve features in photoresist below classical fringe spacing in proof-of-concept chips. And entangled photon ranging has imaged layered tissues with crisper layer boundaries under the same spectral budget. The deepest lesson hiding underneath the hardware is about where limits come from. Diffraction is not a policeman. It is a bookkeeping rule about how much distinct spatial information a given field carries. Classical light carries one kind of bookkeeping, quantum light carries another. And when you engineer the latter, by locking photons together, asking your detector smarter questions, or silencing the right kind of noise, you change how much usable detail rides home in the data, even though the lens and wavelength haven't changed. In other words, the wall is real if you march straight at it with ordinary assumptions, but there are doors cut into it, and the handles are labeled correlation, conditioning, and careful counting. And if you keep the ethical dimension in view, many of the most exciting gains arrive at lower dose. With fewer photons actually striking the specimen, you start to see a philosophy as well as a technology. Clarity does not always come from brightness. Sometimes it comes from clever light, the kind that carries more meaning per photon, so that the smallest structures you care about can finally show themselves without paying the heavy price of being seen. Delayed eraser with quantum memories. You're told you can make a decision after a photon has already been detected and still change whether a wave-like pattern appears in your data, and it sounds like a cheat until you see the actual machinery. Not a time machine, but a quantum memory. A tiny vault that can hold the partner of your detected photon long enough for you to choose what kind of question to ask later. So the experiment becomes a story about what information you keep, what you erase, and how those choices sculpt the patterns you can extract from the past without ever rewriting a single event. In practice, it begins with pairs of photons created together, so they share a delicate link. One, the signal, is sent through a two-path device that would show interference if nothing leaves a trace of which route it could have taken, while the other, the idler, is captured in a memory made of atoms or a crystal that can store a light, field as a collective whisper of matter, an excitation spread over many particles that remembers phase as faithfully as it remembers presence. The magic of the delay comes from the fact that the signal photon is measured first. Its arrival time and position are recorded by a detector that cannot, on its own, show interference because the apparatus has been arranged so that the two routes are in principle distinguishable. Then, only after this click is safely logged, you decide what to do with the idler that's been waiting in the memory. If you choose to read the memory in a basis that reveals which path, information, say the memory has stored a polarization tag or a time bin label tied to the signal's possible routes, then when you correlate the stored partner's outcome with the earlier signal detection, the combined data behave like particles that took one path or the other. No fringes emerge in the coincidence counts when you sort by those path labels, but if you rotate the memory's readout so that it no longer reveals the tag, effectively making the two possibilities indistinguishable, then, when you go back and pair each earlier signal click with the later idler readout, a wave-like pattern appears in the coincidences. In some settings, you even see complementary fringes and anti-fringes, depending on which erasing outcome you post-select from the memory. Nothing about the signal detection changed retroactively. What changed was your ability to group earlier events into sets whose statistics carry interference, or sets whose statistics don't. And that ability depends on whether the memory preserved the phase link or exposed the path mark. For this to work, the memory must do more than hold a timestamp. It must keep coherence, the relative timing of those invisible ripples, so that when you finally shine the control beam to retrieve the idler, the released light still carries the right relationships to interfere with your analysis choices. Researchers achieve this with electromagnetically induced transparency in cold atomic clouds, with Raman schemes in warm vapor, or with rare earth-doped crystals chilled to hush their internal noise, each acting like a pause button for quantum states, over microseconds to sometimes milliseconds. The laboratory choreography is deliberate. You time tag every signal detection with nanosecond precision. You store the idler for a controllable delay, and a high-speed random number generator chooses the readout basis after the signals click. That choice drives wave plates or phase modulators before the memory is emptied, guaranteeing the decision is made later and locally. When you finally plot coincidences, pairing each early click with its matching late partner, you see that the subset corresponding to erased information forms bright and dark bands, as if the signal had been free to be a wave, while the subset corresponding to revealed information stays flat, as if it had been a particle with a definite route. Yet if you ignore the memory entirely and just look at all signal clicks by themselves, there is no interference at all. That last fact protects causality. No one at the signal station can tell from local data which basis will be used later in the memory. The fringes appear only after you bring both records together and sort them, which means there is no faster-than-light messaging and no influence creeping backward in time. Reality here is not being rewritten. Records are being reorganized according to whether the world kept path marks or allowed them to blur. The imperfections are instructive rather than disappointing. If the memory adds too much noise, the eraser loses power because random background counts wash out the neat pairing. If the storage time gets long compared to how quickly the atoms drift or dephase, the phase link fades and visibility drops. If the tagging of paths is incomplete, you'll see partial fringes in both bases because the world never kept a clean ledger to begin with. Calibrations matter. You characterize memory efficiency, verify that the retrieval actually respects the chosen basis, and measure how visibility changes with storage time to quantify how well coherence survives. You also design the which path tags to be removable, often encoded as polarization or time labels, so that a simple basis. Rotation truly erases your ability to know the path rather than just hiding it behind technical clutter. The delayed eraser with memories is not just a curiosity. It demonstrates tools you need for quantum networks, storing photonic states so distant labs can wait for one another, choosing measurement bases adaptively after heralds arrive, and proving that entanglement can be parked in matter and later returned to light without losing its appetite for interference. It also sharpens a conceptual point you can carry far beyond optics. What you can learn from a system is shaped by the availability of distinguishing records. When such records exist, even if no human ever reads them, the universe behaves as though paths were exclusive. When the records are engineered to be uninformative, possibilities blend into patterns that only show up when you ask the right joint question. And perhaps the deepest takeaway is gentle rather than dramatic. The past is fixed, but its meaning is elastic because meaning belongs to patterns within data, and patterns depend on how you combine pieces. The memory doesn't let you edit history, it lets you decide which history you're able to see, reminding you that in both physics and life, clarity is often not about collecting more facts, but about choosing which traces to keep, which to let go, and how to pair them so a hidden picture finally comes into view. Quantum switch experiments in the lab. You're used to the comfort of sequences. Do this, then that, cause, then effect. So it's disorienting to stand in a lab and watch an experiment whose whole point is to let two operations happen in both orders at once, and to realize that the payoff isn't science fiction, but real. Practical advantages, cleaner communication through noise, sharper discrimination of black box devices, and new levers for sensing, all born from a machine called the quantum switch that treats before and after as options you can place in superposition rather than as a hard rule carved into time. The idea sounds abstract until you look at the hardware, where a single photon is prepared in a superposition of two counter-propagating routes around a loop, so that in one route, the photon encounters device A and then B, while in the other it meets B and then A. And because the photon inhabits both routes at once, The overall process, A then B and B then A, coexist in a controlled way that you can read out at the end with a pair of detectors. In the most common photonic version, the photon's polarization acts as the control qubit that decides the order, and its path carries the system on which the devices act. You set horizontal polarization to send the photon clockwise and vertical to send it counterclockwise. Then you prepare a balanced superposition of horizontal and vertical so that both histories are live. What A and B actually do can be anything from simple waveplate rotations to opaque black boxes provided by a colleague, phase shifters, partial polarizers, even intentionally noisy filters, because the switch is a higher order arrangement. A device that doesn't change A or B internally so much as it changes how the order of A and B is wired together. The first conceptual hurdle is honesty about what's new. This isn't a time machine, and it doesn't let you message your past self. Within each branch of the setup there's a perfectly ordinary order, and no single detector sees paradoxes. The novelty lives in how the two orders are combined and in the tasks where that combination carries extra power, much like how entanglement doesn't break locality but still lets you perform feats impossible with independent particles. One such feat is channel discrimination with fewer queries. Suppose A and B are unknown black boxes that either commute or anti-commute. With a definite order, you need a certain number of trials to tell which case you're in, but with a quantum switch, a single round can imprint a telltale pattern on the photon's control that exposes the answer more quickly, saving precious samples or time. Another feat is communication through noise that would otherwise be useless. There exist pairs of very lossy or randomly scrambling operations that, in any fixed sequence, erase a message completely. Yet when placed in superposition of orders, the same photon emerges with a faint but readable trace of the encoded bit, turning a pair of mute channels into a whispering line. And a third is metrology with stubborn instruments. When A and B carry small, hard to untangle distortions, their superposed orders can turn those nuisances into clean, separable signatures on the control, making weak parameters easier to estimate without cranking up power. To turn these promises into numbers, experimentalists need more than pretty stories. They need certification that the device really used indefinite order rather than a hidden classical switch, flipping between A then B and B then A. The tool for that is a causal witness, a measurable quantity that, like an entanglement witness, can go negative only if the underlying process can't be decomposed as a probabilistic mixture of definite orders. Building and violating such a witness requires careful tomography of how different inputs and readouts correlate. And when the witness dips below the classical limit, you've earned the right to say your machine is causally non-separable. It realized an order that wasn't merely uncertain but genuinely indefinite. The optics that make this possible are tangible and fussy. A Sagnac loop keeps the two directions matched down to sub-wavelength imbalances so that the photon's clockwise and counterclockwise stories remain synchronized long enough for you to recombine them. Electro-optic modulators inside the loop implement A and B as programmable polarization or phase changes at nanosecond timescales. Beam displacers and polarizing beam splitters route the control and system cleanly so that crosstalk doesn't leak which order information into stray modes. And time-tagging electronics record arrivals with picosecond precision so that you can slice the data by settings and expose the promised advantages. There are non-photonic flavors too. Trapped ion teams have treated two gate sequences on an ion's internal state as A and B and used a phonon or another qubit as the order control, demonstrating gate ordering superpositions without light at all. Superconducting circuits and acoustic platforms are exploring similar architectures where microwave pulses or mechanical drives play the roles of A and B. These variants matter because they show the concept isn't a quirk of optics. It's a resource that different platforms can borrow to solve their own problems. With power comes fragility. Tiny losses or phase drift inside the loop can tag the roots differently, ruining the delicate cohabitation of orders. Imperfect extinction in polarizers quietly leaks which path hints that degrade the witness. Thermal creep in the table can bias the statistics so that an apparent advantage melts after long runs. Protecting the effect means isolating vibrations, stabilizing temperature, balancing insertion losses of A and B, and validating that any advantage persists under blind swaps where the labels of A and B are secretly exchanged to catch unconscious tuning errors. Perhaps the subtlest lesson for your intuition is that order itself is a resource you can engineer, just as you once learned to think of polarization or spin as carriers of information. Here you learn to treat what comes first as something you can control, store, and entangle with other properties. Once you see order as programmable, you notice problems where rearranging steps in a superposed way saves effort. Not because nature dropped causality, but because causality in quantum theory allows global arrangements that have no classical analog. And when you step back from the racks of optics and the hum of detectors, there's a softer reflection to keep. Most of your life runs on rails of habit, A then B, always in that order. Yet the lab hints that some limits are fences only because you never tried opening the gate. By asking the system to carry two possible sequences at once, you extract answers that neither sequence alone would yield, and you do it without violating the past or inventing miracles, only by choosing the frame in which questions are asked. In physics, that choice is physical, implemented with crystals and modulators, and in thinking it is mental, implemented with willingness to reorder the steps you took for granted. Either way, the switch is the same. Not a gadget to break time, but a disciplined invitation to let before and after share the stage long enough for something new to be said. Loopholes, slamming shut. You can tell a field is maturing when the excuses dry up. And in quantum physics, the most famous excuses had friendly names. Loopholes, little escape hatches that let a skeptic say, maybe those spooky correlations aren't truly beyond classical explanations. Maybe you just missed something. So imagine walking into a lab where each of those hatches has been bolted shut with hardware, timing and statistics so strict they feel like a courtroom. And your job is simply to watch how carefully people remove every ordinary way out until the only remaining story is the uncomfortable one. Nature really does produce correlations no local, pre-agreed plan can explain. Start with why anyone needed loopholes at all. When two distant labs measure their halves of a pair prepared together, the results align more tightly than any scheme of hidden instructions handed out in advance would allow. That is the crux of Bell's insight, a bound on how correlated classical, separate realities can be. And the experiments keep finding violations of that bound, but early tests were vulnerable. Detectors missed many particles. Switches were slow, clocks were sloppy, and data selection gave wiggle room. So a critic could always say, your sample was biased, or signals had time to sneak across, or your settings weren't truly free. The modern push is a quiet engineering marvel. You increase detector efficiency so close to perfect that missed events can no longer hide a classical conspiracy. You separate stations far enough and switch measurement settings fast enough that even light couldn't carry a last-second message from one side to the other. You generate setting choices with physical randomness that's independent of the source. You define when a trial starts and ends so clearly that clever coincidences can't inflate the score. And then you analyze the full record with methods that tolerate finite data and memory effects, refusing to cherry-pick the best rounds. The detection loophole was the oldest refuge. If your detectors only click for some fraction of the pairs, maybe the detected subset had special properties that make quantum look good. So teams built brighter, purer sources and paired them with superconducting nanowire single-photon detectors. Devices kept so cold, they turn a single photon's crossing into a crisp electrical pulse with efficiencies above what the theory requires. Elsewhere, trapped ions and defect centers in diamond used near-unit detection of internal states, removing the need to guess what the missing events would have said. When almost every trial yields a result, the fair sampling assumption moves from hope to measurement. The locality loophole was a geography problem. If settings on one side are known in time for a light speed signal to cross the gap before the other side finishes, perhaps the device is whispered, and the answer was to go wide and go fast. Stretch the stations to hundreds of meters or kilometers, synchronize them with atomic clocks or GPS, and flip the measurement bases with electro-optic modulators driven by fast random bits arriving just before each detection. Under those conditions, the space-time diagram tells a simple story. There is no overlap where a causal signal from A could reach B in time, or vice versa, so any explanation that relies on last-moment coordination cannot apply. The freedom of choice loophole asked whether the random settings were truly independent of the particles being measured, if a hidden variable could secretly influence both. A local model might mimic quantum, but the response has been delightfully literal. Use randomness pulled from physical processes far removed from the source. Phase noise in lasers, radioactive decay, even colors of light from distant stars and quasars whose emissions began long before the experiment, and route those bits into the fast switches. The further back in time you push the origin of your randomness, the less plausible it is that a single common cause arranged both the settings and the microscopic states mere microseconds ago. You can't disprove exotic worldviews that deny randomness altogether, but you can choke off ordinary dependencies until only philosophical outliers remain. The coincidence time loophole played on bookkeeping. If you define pairs by whether their detection times happen to fall within a chosen window, you might inadvertently select only those events that look quantum and discard the rest. So newer tests avoid post hoc pairing and use event-ready heralds. The source signals a valid pair exists now, or an entanglement swapping node lights a flag, and only those flagged rounds count. With trials framed this way, shifting the coincidence window cannot morph failure into success. The memory loophole suspected that devices might learn from previous rounds and game the statistics, so analysts adopted techniques that do not assume independence between trials, using martingale bounds and other finite data tools to assign conservative confidence levels. The result is not a flashy graph, but a sober p-value that stands even if the apparatus had a long, imperfect memory. Layered on top of the main offenders are smaller cracks you still seal. You blind the analysis team to which dataset will be used, so unconscious tuning doesn't help. You test that swapping the labels of settings or detectors leaves the violation intact. You publish pre-registered analysis plans to prevent retrospective phishing. Across platforms, the story converges. Photons let you span city blocks and prove space-like separation. Solid-state defects and trapped ions give you near-perfect detection with exquisite control. And hybrid networks perform entanglement swapping that combines both virtues. The details differ. Wavelengths, materials, cryostats, but the logic is the same. Remove the mundane exit routes and see what remains. When you step back, the conclusion isn't that messages leap faster than light, or that cause and effect are broken. The experiments still obey the rule that no station can use its setting to signal the other. It's the joint statistics, revealed only when you bring both logs together, that break classical bounds. Quantum theory predicted these numbers for decades, but seeing them survive hostile cross-examination changes how you trust the theory. It's not just elegant, it's resilient. Do loopholes ever end? There's one that's more a posture than a path in the lab. Superdeterminism. The suggestion that every setting choice was secretly coordinated with hidden variables from the beginning of time. Because it explains everything by assuming everything was fixed, it predicts little and evades most tests. So experimentalists keep tightening ordinary independence and let that remaining possibility live where it belongs, in debate rather than in data. What all of this teaches you beyond the headlines is a method for thinking. When a claim makes your gut uneasy, list the concrete ways it could be faked. Bias, leakage, selection, dependence, and then design the world so those ways are unavailable. In the Bell saga, that discipline produced a chain of experiments whose only common outcome is that the universe prefers quantum bookkeeping to classical plans. And the soft lesson is personal as much as physical. Doubt well, doubt specifically, and then let careful closures tell you when doubt has done its job. Eventually the doors stop rattling, the hatches stay shut, and you're left with the strange luminous fact standing in the open. Separated things can be linked in a way no local story can rehearse. And the right response is not to lower your standards, but to raise your attention. Because sometimes reality passes every test you can throw at it, and still refuses to be ordinary. Device-independent randomness certified. Imagine being asked to prove a coin toss is fair when you're not allowed to inspect the coin, the hand that flips it, or even the room where it happens, and somehow still walking away with a guarantee that no one, not even the person who provided the coin, could have predicted the outcome better than chance. That is the audacious promise of device-independent randomness certification, where you treat your hardware as an untrusted black box and lean instead on a handful of physical principles: separation, no messaging faster than light, and statistics that defy any pre-written script, to certify that the bits you harvest are genuinely unpredictable to anyone outside your lab. The road to that promise begins with a setup that looks more like an audit than a gadget demo. You place 2 measurement stations far enough apart that a light speed signal can't shuttle between them during a single trial. You feed each station a fresh, rapidly chosen setting, and you record the 2 outcomes. On paper, you're just sampling correlations. But the trick is which correlations you look for, because there is a region of results that no hidden plan assigned in advance to the 2 devices can reach. If your data land in that region by a healthy margin, you've witnessed non-classical correlations that any classical prearrangement would fail to mimic. And that gap is the lever that pries open unpredictability. From a randomness maker's point of view, that lever is turned into a bound on predictability. If a hypothetical eavesdropper had built your boxes and knew everything about their guts except the last instance independent settings, how well could they guess the outcomes? Better than a coin, or not? The measured violation of a Bell-style constraint answers that question quantitatively, giving you a guaranteed floor on how much surprise lives in your raw data per trial, even allowing for the real-world warts of finite sample sizes and imperfect detectors. But raw surprise is not yet uniform randomness. So the next stage is extraction, which is less romantic but just as crucial. You feed the messy bit stream and a tiny seed of ordinary random bits into a mathematical extractor, a kind of centrifuge for entropy, and out comes a shorter stream of nearly ideal bits whose deviation from perfection can be kept as small as you like. Because the certification step has already told you how much true unpredictability is present, you can size the extractor conservatively and attach a confidence level that survives outside scrutiny. The elegance of the device-independent approach is what it doesn't assume. You don't need to trust the factory that made your detectors. You don't need to model every stray reflection in your optics. And you don't need to believe that your devices faithfully follow a textbook. You only assume that the 2 stations can't coordinate during a trial, that your setting choices are not secretly leaked to the devices beforehand, and that your lab's boundary holds. Within those mild guardrails, the statistics themselves do the talking. Turning this into a working engine adds layers of care that rarely make headlines, but decide success. You define trial boundaries with nanosecond precision so that start and stop are unambiguous. You pick setting choices with a high-speed source that isn't correlated with the devices, ideally based on physical noise and routed to the stations just in time. You choose detectors efficient enough that missed events can't give a classical model room to hide. You track drifts with timestamps and use conservative analyses that remain valid even if the devices remember previous rounds. And you lock in an analysis plan before collecting data to prevent unconscious cherry-picking. Once those pieces are in place, the protocol can do more than just generate a handful of certified random bits. It can expand and even amplify randomness in ways that are practically valuable. With expansion, you start with a short, ordinary seed and produce an arbitrarily long stream of certified bits, the cost being only time and trial count. With amplification, you begin with a weak, somewhat biased source of randomness, the kind that an ordinary extractor can't save on its own, and, by routing its output into the setting choices of your 2 stations, you promote that shaky seed into a much cleaner product, because any attempt by an adversary to exploit the bias still has to respect the no communication rule during each trial, and therefore can't emulate the non-classical correlations you measure. The everyday uses of such bits are much less flashy than the physics behind them, but no less important. Cryptographic keys that need to be unpredictable even to the vendor who sold you the box that made them. Public randomness beacons for lotteries, audits, and scientific challenges, where trust must come from methods rather than brands. Monte Carlo simulations where subtle correlations in a pseudo-random generator could skew results. And on the horizon, distributed protocols where multiple institutions contribute their own untrusted devices and jointly certify a pool of randomness that no single participant controls. The approach is not free of trade-offs. You burn experimental time and infrastructure to buy independence from hardware assumptions. You accept lower bit rates than a fast pseudo-random generator would offer. You design around fragility because a hiccup in timing or a drop in detector efficiency shows up directly as a weaker guarantee, and you keep your claims honest by folding all those imperfections into the certified bounds rather than hand-waving them away. But the philosophy you carry out of the lab is worth the effort. Trust in outcomes that cannot be faked by design. Trust in methods that survive adversarial thinking. Trust in numbers that come with explicit confidence rather than casual assurance. When you watch the final extractor spit out a stream whose quality is certified by impossibility proofs instead of by brand labels, you feel the difference between marketing and physics. And there's a deeper intellectual nudge here too. We often confuse transparency with security, imagining that only devices we fully understand can be safe. Device-independent randomness flips that instinct on its head and shows that, with the right space-time discipline and the right statistical test, you can get stronger guarantees because you refuse to look inside, forcing nature to vouch for your unpredictability in a language even a skeptical outsider accepts. It's a quiet kind of power. No flashy equations on the wall, no mystical claims about the universe, just the steady closing of ordinary loopholes, the careful counting of trials, and the confident sense that the next bit in your hand was not written down in anyone's notebook before you pressed start. Quantum dots as on-demand single-photon guns. You don't usually think of a crystal as something you can press for a single particle of light on cue, yet that's exactly what a modern quantum dot can do. Act like an artificial atom that, when nudged just right, emits one, and only one, photon at a time with a reliability that turns delicate quantum experiments into push-button routines. And to feel why that matters, you have to look closely at what a quantum dot is and how engineers coax it into behaving like a tiny, disciplined light gun instead of a random spark. A quantum dot is a speck of semiconductor so small that electrons and holes are trapped as if in a three-dimensional box. That confinement breaks the broad, messy energy bands of a bulk crystal into discrete levels, much like an atom's. So when you excite the dot, either with a faint laser pulse or a small electrical jolt, it forms an exciton, a bound electron hole pair that quickly relaxes and then recombines, releasing its energy as a single photon before the dot resets to its ground state. That reset is the secret behind single photon behavior. Once the exciton recombines, there's no second pair waiting to emit again immediately, so the light stream coming from a well-prepared dot shows anti-bunching, a measurable dip in the chance of two photons arriving together. And if you trigger the excitation with a clocked pulse, you can make the dot fire one photon per tick, like a metronome for quantum optics. In the lab, this on-demand control comes in flavors that mirror your goals. Resonant driving aims a laser tuned exactly to the dot's transition, so it flips the dot from ground to excited and back with exquisite timing, reducing the random jitter that otherwise blurs emission. Electrical injection builds the dot into a tiny diode, so a voltage pulse does the same job without an external laser, creating chip-level single-photon LEDs that promise simpler packaging. B-exciton cascades prepare two excitons that decay in a chain and can produce entangled photon pairs when the crystal's internal quirks are tamed, useful for secure communication and quantum networking. Pure single-photon output is only half the story. The other half is indistinguishability. For many quantum information protocols, two photons born at different times must behave as if they are twins so that, when brought together, they interfere perfectly. Quantum dots help here because their emission can be made transform limited, set mainly by the natural lifetime, if you reduce the ways the dot talks to its noisy surroundings. That's where careful engineering steps in. Embed the dot inside a microcavity, a tiny optical resonator between high reflectivity mirrors or within a photonic crystal, so the dot couples strongly to a particular mode. This both speeds up the emission so the photon leaves before environmental jitter has time to scramble it, and funnels the light into a well-defined direction that a fiber can catch. The result is a bright stream with high purity and high indistinguishability, the trifecta that spontaneous down conversion sources, while beautifully simple, struggle to deliver all at once because their emission is fundamentally probabilistic. None of this works without taming the dot's bad habits. Charge noise in the surrounding material can tug the dot's energy levels back and forth, making each photon slightly different in color. Phonons, the crystal's tiny vibrations, can blur the emission if the decay is slow. and spectral diffusion drifts the line over minutes as wandering charges settle. Modern devices fight these, with a PIN diode structure that stabilizes the dot's charge environment, with temperature control that calms vibrations, with clean resonant excitation that avoids making extra carriers in the neighborhood, and with active stark tuning, tiny electric fields that nudge the dot's line back into alignment with the cavity or with another dot. Extraction is another battlefield. Photons naturally want to slosh around inside high-index semiconductor like light in water, so teams sculpt micropillars, nanowires, and parabolic antennas to pick the photon up and throw it out efficiently into free space or directly into an optical fiber. With these tricks, state-of-the-art sources report that almost every pump pulse yields a detected single photon, with the probability of a 2-photon mistake pushed down to parts per 100 or better, and twin photon interference visibilities high enough to power complex multi-photon experiments. Because you don't live in a single wavelength world, materials science offers options. Indium arsenide, dots in gallium arsenide are workhorses around the near-infrared, great for tabletop experiments. By switching to indium phosphide hosts and adjusting dot composition, teams push emission toward the telecom bands used in fiber networks so single photons can travel kilometers with low loss. Strain tuning platforms press gently on the chip to fine adjust the color of each dot and even erase tiny internal asymmetries that would otherwise spoil entanglement in the Biexciton cascade. And site-controlled growth techniques plant dots at predefined locations so that future chips can route many identical sources into complex circuits without playing hide-and-seek under a microscope. All of this may sound like boutique physics until you see what having a deterministic single-photon source unlocks. In linear optical computing schemes, you need streams of identical photons to interfere across many beam splitters. Every time two arrive together at a device, the quality of their interference sets how well the overall computation works, and replacing probabilistic sources with triggered dots is the difference between rare lucky multi-photon events and a steady, scalable supply. In Boson sampling and other near-term demonstrations of photonic advantage, dots have already shown that coordinated clocked photons can push experiments beyond brute force simulation. In quantum key distribution, a true single photon gun removes the need for elaborate decoy tricks designed to hide the multi-photon tail that laser pulses inevitably carry. And in quantum repeaters, dots that entangle their internal spins with emitted photons offer a route to building long-distance entanglement step by step, especially when paired with memories and frequency converters that bridge the gap to telecom fibers. The picture is honest as well as hopeful. Most high-quality dot sources still prefer cryogenic temperatures, so that phonons and charge wander are quiet, which means refrigerators and careful thermal design. Coupling to cavities requires precise alignment that must survive packaging and transport. Scaling to dozens of perfectly matched sources demands uniform growth and post-fabrication tuning across a wafer, not just one golden device. And integrating dots with silicon photonics, the platform where mass-market photonic circuits live, requires hybrid bonding and clever designs to reconcile different materials and refractive indices. These are engineering challenges, not showstoppers, and every year the community reports higher brightness, better stability, and sources delivered in fiber-coupled modules rather than fragile lab mounts. If you want a feel-good litmus test for single-photon gun status that doesn't rely on heavy jargon, it's this trio. When you split the source's beam and look for simultaneous clicks in both arms, that coincidence rate near zero at short delays tells you 2 photon events are rare. When you send successive photons into a device that compares them, their tendency to exit together rather than separately tells you they're nearly identical. And when you pump the source at a steady rhythm, and your counts follow that rhythm without missing many beats, you know on demand is more than a slogan. Step back, and a simple idea shines through the acronyms and cryostats. By carving a tiny island in a sea of crystal and teaching it to talk politely to an optical cavity and a clean power supply, you turn light from a flood into a faucet, from maybes into pulses you can count on. That shift, from abundance to control, is exactly what moved electronics from sparks to logic a century ago. And it is what will move photonics from pretty demonstrations to machines that compute, communicate, and secure information one irreducible quantum at a time. And there's a human echo in this controlled glow. Clarity often arrives not by making more, but by shaping what you already have, so it comes out one piece at a time when called in the form you can actually use. A quantum dot's calm, single heartbeat of light is a reminder that precision is a kind of kindness to your measurements, to your networks, and to any future where information rides the smallest possible carrier and still arrives exactly as intended. Spin squeezing, beating the shot noise limit. You learn early that measurement noise has a flaw you can't dig through. Count, identical atoms acting like tiny compass needles, and the uncertainty in their collective direction falls only as 1 over the square root of n, a ceiling called the shot noise or standard quantum limit, and it feels as fixed as gravity until you watch a cloud of cold atoms in a vacuum chamber do something sly. They don't get quieter by adding more atoms. They get quieter by rearranging their quantum noise, squeezing it away from the quantity you care about and into a direction you're willing to sacrifice. And in that trade, you suddenly measure angles more sharply than the old limit allowed. Picture the ensemble's total spin as a single arrow on a sphere, not a hard arrow, but one girdled by a fuzzy noise belt that reflects the unavoidable quantum jitter of many uncorrelated atoms. In an ordinary Ramsey measurement, 2 gentle pulses separated by a weight in which a field imprints a phase. That belt sets how precisely you can read the arrow's final tilt. Spin, squeezing tightens that belt along one axis while letting it bulge along the perpendicular one. You narrow the uncertainty in the quadrature you read out, the metrology axis, and accept extra uncertainty in the conjugate quadrature you ignore, obeying quantum rules yet sidestepping the classical averaging law. There are 2 broad ways you see this done in the lab. In measurement-based squeezing, you send a very weak off-resonant pulse of light through the atoms and let it pick up a whisper of their spin as a phase shift. Reading that phase gives you information about one spin component without flipping the atoms much. A quantum, non-demolition glimpse, and the act of learning collapses the ensemble into a narrower distribution along that component. The price you pay is back action that puffs up the orthogonal component, the anti-squeezing. But if your sensors care only about the narrowed direction, you come out ahead. In interaction-based squeezing, the atoms are made to talk to one another so their small jitters become correlated. Collisions in a Bose-Einstein condensate, spin-dependent forces in trapped ions, or light bouncing many times in an optical cavity create an effective twisting of the noise belt, often called one-axis twisting, that shears the circular fuzz into an ellipse whose short axis is the squeezed one. With clever control, even 2-axis counter-twisting is possible in principle, which would squeeze faster and further. Both routes are practical, both are noisy in their own ways, and both have delivered genuine metrological wins. To feel the payoff, return to the Ramsey clock picture you've seen in every metrology textbook and update one step. Instead of preparing a simple coherent spin state, you prepare a squeezed one before the free evolution. Now the same tiny phase shift from a weak magnetic field or an optical transition rotates the arrow by the same small angle. But because your uncertainty along the readout axis is narrower, the same angle produces a larger signal-to-noise ratio in fewer trials. Said in plainer language, with squeezing, you get the same precision with less averaging time, or better precision in the same time. In atomic clocks, that means smaller Allen deviation plots for a fixed atom number. In magnetometers, it means detecting weaker biomagnetic currents or faster neural dynamics without jacking up the probe light and cooking the sample. You'll hear a compact figure of merit. If the variance of your readout falls below the standard quantum limit by a factor r, people call that 10 log 10 r decibels of squeezing. Several platforms have now shown more than 10 decibels, an order of magnitude cut in projection noise, while still keeping contrast high enough to matter in a full measurement cycle. Under the hood of those data are concrete engineering choices. Cavity-based QND squeezing uses mirrors with extreme reflectivity, so a probe beam samples the collective spin thousands of times without absorbing much. Then a fast homodyne detector reads the phase, and real-time feedback rotates the ensemble to park the squeezed quadrature exactly where the next Ramsey pulse will read it. Beck-based squeezing times the interaction so the twist stops at the optimal moment, before the ellipse overshears and wraps around the sphere. Ion chains create pairwise couplings with laser-driven forces that imprint just the right correlated jitter to shrink the metrology axis. Every knob has a cost. Make the probe stronger, and you learn the spins sooner, but you also scatter more photons and decohere the atoms. Twist longer, and you squeeze more, but you also amplify any inhomogeneity in how atoms couple to light or to each other. Let technical noise creep into the detection, and you hide the win under classical clutter. Honest teams therefore publish not only the dB of squeezing, but also the Wineland parameter, metrological benchmark that folds in contrast and tells you whether the state is actually useful in a Ramsey sequence, and they run head-to-head comparisons. Same atom number, same interrogation time, squeezed versus not. Clock stability or field sensitivity plotted over minutes to hours. One of the quieter, deeper truths you absorb as you read these papers is that squeezing is entanglement you can use. When the right squeezing parameter drops below unity, the atoms aren't just behaving. They're sharing quantum correlations across the ensemble that no separable model can reproduce. And it's precisely those correlations that let your readout dodge the square root law. The dream limit, phase noise scaling as 1/n, the so-called Heisenberg limit, belongs to extreme states that are fragile in noisy, lossy reality, but squeezing moves the dial steadily toward that dream, with states that survive real interrogation times, imperfect detectors, and busy laboratories. The horizon is practical, not mystical. Squeezed spin states are being woven into optical lattice clocks that already serve as timekeeping gold standards, promising faster comparisons between lab clocks and satellite links. Chip-scale magnetometers are experimenting with spin exchange-free regimes, plus squeezing to push within reach of single neuron action currents and micro-Tesla gradients in living tissue. Even gravitational wave detectors, famous for squeezed light, are exploring whether hybrid sensors that combine light and atoms can share quantum noise reductions across the whole instrument. None of this is a free lunch, and that's the grown-up version of the story you should keep. Squeezing is a budget with line items, less variance here, more variance there, fewer uncorrelated atoms, more shared fate, lower projection noise, tighter tolerances on alignment and stability. And you must maintain that budget across the entire measurement, from state preparation through interrogation to readout, or the advantage leaks away through a dozen small cracks labeled detection inefficiency, inhomogeneous coupling, residual dephasing, and drift. But when the plumbing is tight, the effect is unmistakable. The little dots on your phase plot cluster closer than the textbook said they could. Your confidence intervals shrink without adding atoms, and your instrument reports the world with a calm you didn't know it could afford. The human parallel is gentle. Sometimes the way past a limit isn't to add more of the same. It's to change how the parts you have are allowed to fluctuate. To accept loudness where it doesn't hurt in order to be quiet where it does. Spin squeezing is that principle turned into hardware. A reminder that precision is often a choreography of compromises, and that by choosing which uncertainties to carry and where to carry them, you can hear signals that used to be lost in the hiss and tell time, or feel fields, with a grace that felt impossible before you learned to squeeze. Rydberg blockade. Atoms that know each other. You might think atoms are too small and too aloof to pay attention to one another. Yet there is a regime where a single excited atom changes the rules for its neighbors so dramatically that the whole group behaves like a crowd that hushes the instant one person stands. This is the Rydberg blockade, and it turns a quiet cloud of neutral atoms into a system where who goes first matters so much that only one can go at all. To see why, start with the idea of a Rydberg state, an atom whose outer electron has been lifted far from the nucleus, so it orbits in a giant, delicate cloud, and because that electron is so loosely bound, the atom becomes ridiculously sensitive. Its size balloons, its response to electric fields swells, and its ability to feel other atoms' presence grows from a polite nudge into a shove. Now imagine a line or grid of laser-cooled atoms held in place by tightly focused beams, optical tweezers, so each sits like a glowing dot on graph paper, and you shine a carefully tuned laser that would, if the atoms were isolated, flip them into that giant Rydberg state one by one with clockwork regularity. But the moment the first one makes the leap, its swollen electric character shifts the energy levels of atoms within a certain radius, so they're no longer in tune with your laser, and the flurry of possible excitations collapses to a single allowed one, an invisible keep-out zone expanding around the pioneer. That radius, set by how strongly Rydberg atoms interact and how hard you drive the transition, is the boundary that forces the group to act like a single superatom, meaning the next excitation can only happen outside the blocked region, or after the first one decays back, or after you deliberately move the boundary with your controls. This simple rule, one at a time within arm's reach, sounds like a restraint, but it's the source of power. It lets you build two-atom logic gates by addressing a pair with lasers, where exciting the first retunes the second so you can make if and only if operations that are the backbone of computing. It lets you write and erase many body patterns, checkerboards, stripes, rings, by choosing which tweezers to illuminate so the Blockade sculpts ordered arrangements out of what would otherwise be random excitation. And it lets you create a shared, delocalized single excitation across a small cluster, a collective state that responds faster and more cleanly than any single atom would, because the whole group participates in one coordinated flip. In practical terms, teams build these machines with chilled atomic species like rubidium, cesium, or strontium, trap hundreds or thousands of atoms in rearrangeable tweezer arrays, and then use a two-step laser process to climb from the stable ground level to a selected Rydberg level via a short-lived intermediate stop. The lasers must be narrow in color and steady in phase so the atoms don't wobble off resonance. And the background electric fields must be tamed because even a trace of stray charge on a nearby surface can tug Rydberg levels around. When it all lines up, you can perform a two-atom gate in microseconds, fast compared to how long the atoms keep their ground state memories. And because you can steer tweezers like pixels, you can decide who talks to whom from one experiment to the next, literally redrawing the wiring diagram of your quantum processor on demand. The same strong forces that make Blockade work can be used more gently in what's called dressing, where you mix a little Rydberg character into ground state atoms without fully exciting them. That seasoning spreads soft, tunable interactions across the array, allowing you to mimic the behavior of magnets, lattices with frustration, or exotic phases of matter, and then watch those phases grow and compete under your camera. By adjusting laser detunings and intensities, you can bring two-atom resonances into play, encourage excitations to hop like checker pieces, or create facilitation zones where one excited atom makes it easier, not harder, for a neighbor to join. A deliberate inversion of Blockade called anti-blockade that maps out a different kind of many-body dance. Measuring what you've created is as visual as it is precise. The tweezers serve as both trap and microscope, and after your laser sequence you take a fluorescence picture in which ground state atoms glow and Rydberg atoms sit dark, giving you a snapshot of who flipped and where the Blockade pushed back. By repeating this many times and stitching the statistics together, you see the formation of ordered patterns at certain distances. You watch defects creep and heal, and you quantify how well your gates avoided crosstalk. Any accidental neighbor flips show up as scars you can trace back to timing errors or field noise. None of this is automatic, and the challenges tell you what matters. Blackbody radiation can knock Rydberg atoms down early, so experiments often run at low temperatures or choose levels less exposed. Tiny drifts in laser frequency blur the sharp edge of the Blockade, so teams stabilize their light to reference cavities and constantly recalibrate. Atoms can be lost from tweezers during repeated operations, so atom assembly steps reshuffle survivors to fill gaps, like a robotic hand tidying a chessboard between games. Even the geometry of your tweezer pattern matters because triangles, squares, and honeycombs each define different neighbor distances and therefore different Blockade rules. And engineering those geometries is how you draw a Hamiltonian with light. You might ask whether these atoms really know each other or whether we're smuggling in a metaphor. And that's the teachable moment. Nothing telepathic is happening. What changes is the local energy cost of putting a second atom into the giant state when the first is already there. And because your lasers are tuned to a specific cost, the second atom is simply out of tune until you move the knob or wait. The knowledge is not awareness, but influence encoded in shifted lines and moved thresholds. And the reliability, with which you can turn that influence on and off, atom by atom, is what makes Blockade a tool rather than a curiosity. The story feeds into broader ambitions. Neutral atom quantum computers built on Blockade have already shown prototype algorithms and error-correcting primitives, with roadmaps that connect thousands of tweezers into modular architectures. Quantum simulators use Blockade and dressing to explore problems that otherwise live only in equations, from the growth of correlations after a sudden quench to the constrained dynamics of emerging gauge theories. Single-photon interfaces borrow Blockade to convert a single shared excitation into a clean photon on demand, or to absorb a photon only if one is not already present, laying groundwork for repeaters and network nodes. And sensing schemes explore whether the exaggerated response of Rydberg levels to fields can serve as tiny antennas for radio waves or as probes of stray charge near surfaces. Through all of it runs a theme you can carry beyond the lab. Limits change when interactions enter the room. An isolated thing follows tidy rules, but a thing that strongly shifts its neighbors rewrites the game board as it moves. And with the right discipline, that feedback becomes a resource. One atom protecting a sphere around itself so only one bit of change can happen there at a time. A group of atoms acting like a single amplified degree of freedom. A pattern emerging not from individual intent, but from rules enforced at arm's length. And there is a softer insight too, the kind you feel when the fluorescence image finally appears after a careful run. Control at this scale is not about dominating matter, it's about arranging conditions, so influence flows in simple, predictable ways. Create a boundary, set a timing, let one event make room or close doors for the next, and trust that clarity will emerge from those constraints. Rydberg Blockade is that philosophy in atomic form, a way to make order by asking each piece to leave space for its neighbor. And in that quiet, enforced courtesy you get computation, simulation, and a surprisingly tender lesson in how knowing is sometimes nothing more than letting the presence of one thing reshape what is possible for the rest. Trapped ion cat states you can count. You were told Schrödinger's cat was just a thought experiment, yet in a quiet vacuum chamber, experimenters now draw cats you can actually count, not with whiskers and fur, but with the motion and spin of single trapped ions whose behavior splits, interferes, and then reveals itself one unmistakable tick at a time. Begin by picturing a lone charged atom hovering above tiny electrodes, held by oscillating electric fields in a harmonic cradle and cooled by lasers until its motion is so calm that vibration comes in discrete quanta rather than as a blur. And inside that same atom, a pair of long-lived internal levels plays the role of a two-state system you can flip like a tidy coin. The trick is to make the ion's internal state and its motion talk to each other with a very gentle push from light, a push that depends on which internal level the ion is in. So if you start the ion in a balanced internal superposition, and then apply that state-dependent force, one branch of the superposition gets nudged to the left in phase space, while the other branch is nudged to the right, and the once simple motional wave packet separates into two distinct coherent lumps tied to two internal labels. A genuine cat state of motion you can assemble on command. If you then reverse the steps cleverly, you can park the internal state back where it started and keep only the motional superposition, a supersensitive pointer whose two lobes are far apart compared with the tiny ground state fuzz. And because those lobes are still part of the same quantum state, rather than two classical alternatives, they can be brought back to overlap and interfere, producing fine stripes in phase space that serve as the cat's signature. You don't see phase space with your eyes, so you learn to read it by counting. Displace the motional state by a known amount. Measure a simple property called parity that trapped ion systems can access cleanly, and repeat this across a grid of displacements. The resulting map is the Wigner function, a kind of shadow of the state, and the alternating positive and negative regions, those delicate stripes, tell you not only that the cat exists, but how large it is and how coherent its two sides remain. And you can literally count the stripes to quantify the separation. If that feels abstract, there is a more direct kind of counting that makes trapped ions famous, state-dependent fluorescence, where the ion shines brightly when it ends in one level and stays dark when it ends in the other. So a camera sees yes-no with near-perfect reliability, and by repeating the cat sequence with different analysis phases, you watch the bright fraction swing rapidly as interference flips the outcome back and forth, the number of swings revealing how sharply separated the cat's components are. There is a second meaning to cat you can count, And it involves not one ion, but many, by turning on an interaction that couples every ion's internal state to a shared vibrational mode, often with a laser pattern that amounts to a gentle, global push. You can prepare an entangled superposition where all ions are aligned one way, or all are aligned the opposite way. A many-body cat whose collective phase can be read out through parity oscillations that speed up with the total number of ions. In practice, you see this as a set of fringes so fine that they would be invisible without entanglement. And counting those fringes as you scan an analysis angle lets you estimate tiny shifts with a sensitivity that improves faster than the ordinary square root rule, which is why these states are coveted for clocks, field sensors, and tests of fundamental noise. Building the cats in the first place is a choreography of timing, light, and quiet. The ion is first cooled near its motional ground state with resolved sideband techniques, then a pair of laser beams or a microwave plus magnetic field gradient delivers the state-dependent force for a precise duration. And finally, a reversing pulse sequence recombines the branches or maps the motional interference back onto the internal states so your detector can see it. The same toolbox lets you switch between a pure motional cat and a many-ion cat by changing whether the shared motion is just a bus for entangling spins or the object of the superposition itself. You verify that you have not fooled yourself by running number-resolving tests, drive a red or blue sideband and watch how the transition strengths line up with the expected distribution of motional quanta, or by reconstructing the Wigner function and checking for the telltale negativity that no classical mixture can imitate. These cats are not party tricks, they make instruments bolder. A motional cat converts a tiny force or a brief acceleration into a large, readable phase because the two lobes feel opposite kicks. So accelerometers and force sensors based on a single ion can register signals that would drown in ordinary thermal jitter. And a many-ion cat composed of internal states can serve as the heart of a precision measurement where the phase evolution under a weak field is amplified by the entanglement shared across the register, letting you reach a target uncertainty in less time or with fewer particles. In both cases, the point is not to violate any limit, but to move your meter to a place where nature's noise is kindest to the quantity you care about. The vulnerabilities are as educational as the wins. As you separate the lobes further, the environment gets more chances to learn which way the ion went through stray electric fields, drifting trap frequencies, and the gentle hum of blackbody radiation. And every such leak steals contrast from the interference. To fight that, teams operate traps at cryogenic temperatures to calm electric field noise. Choose magnetic field insensitive internal transitions so slow drifts don't imprint random phases, shape their laser pulses to avoid off-resonance scattering, and even use a second helper ion of a different species to cool away heating without ever looking directly at the cat. When the laboratory is kind and the choreography is sharp, cats that once lived for microseconds now survive long enough to be practical sensors and reliable building blocks for entangling gates. Perhaps the most surprising part, when you finally internalize it, is how concrete the evidence becomes. There is nothing mystical in the record, only arrays of bright and dark outcomes whose statistics draw interference patterns as clearly as ripples on water. Parity curves that rush through multiple zero crossings as you sweep an angle knob, and phase space maps whose counted stripes tell you how far apart your lobes wandered before they returned to greet each other. You leave the chamber with a different sense of the old fable, because here, the cat is not a metaphor for indecision, but a quantifiable resource you can create, stretch, shrink, and deploy. And your faith in it rests not on stories, but on counts that hold steady under repetition and under deliberately inserted cross-checks. And in that steadiness lies a softer lesson that reaches beyond physics. The most delicate forms of clarity do not arrive by staring harder, but by preparing conditions in which two possibilities can take distinct paths and still be brought back to speak to one another. When you give them that chance and listen in the right basis, even a single atom can sketch a pattern that persuades you without drama. Lines you can count, fringes you can trust, and a cat that teaches you gently that uncertainty is not ignorance but the raw material from which precision is made. Entangled microwaves in superconducting circuits. You don't expect something as homely as a few gigahertz radio wave to behave like clasped hands that keep squeezing and relaxing in perfect unison. Yet that is exactly what you watch happen inside a silvered can at the bottom of a dilution refrigerator. Two microwave fields, born together from a sliver of superconducting nonlinearity, share fluctuations so tightly that what one gains, the other loses, and their joint breathing carries a signature no classical static can imitate. To understand why that matters, start with the setting, where aluminum or niobium traces cool to a few millikelvin shed electrical resistance and act like frictionless highways for currents, and where a special ingredient, a Josephson junction, just two superconductors separated by a nanometer-thin barrier, behaves like a spring whose stiffness depends on the current through it, letting engineers build parametric devices that trade energy between tones, the way a child on a swing trades height and speed. If you pump such a device at just the right frequency, the nonlinearity splits that pump into pairs of lower frequency photons, two microwave quanta that fly down separate transmission lines, but keep their quadratures correlated in a way that, when measured together, looks like shared certainty beyond what independent noise would allow. You read that certainty not with a camera but with mixers and clocks. Each output is amplified by near quantum limited stages and then compared to a stable, local oscillator to extract the instantaneous quadrature values. Think of it as turning an invisible oscillation into two slowly varying voltages, one saying how far east-west, and the other how far north-south the field leans in phase space. And when you plot many such samples from the two lines, you find that certain combinations are exceptionally quiet, quieter than any pair of independent vacuum states could be. That quietness is how you witness entanglement in the continuous variable world of microwaves. And because it is statistical rather than a single breathtaking event, you can quantify it rigorously using covariance matrices, entanglement witnesses, and tomographic reconstructions of the joint Wigner function that reveal the noise squeezed into an ellipse whose axes tilt across the two modes. The hardware that makes this possible wears many names but shares a heartbeat. Josephson parametric converters that couple two resonators through a flux pump junction and deliver clean two-mode squeezing. Traveling wave parametric amplifiers that send a pump down a long engineered transmission line so fresh entangled pairs are born at every step, and the output emerges as bright broadband twin beams. And hybrid interferometers that split, delay, and recombine itinerant microwave modes to test how far the correlations reach. The parts are surprisingly tactile. Waveguides and coax cables set with attenuators to thermalize stray room temperature noise. Cryogenic isolators and circulators that enforce one-way traffic so the delicate states aren't pummeled by their own reflections. And calibration tones that let you count exactly how many photons of noise each amplifier adds, so you never mistake a good day in the fridge for a miracle. The need for extreme cold isn't ritual, it's arithmetic. A 6 GHz photon corresponds to a few tenths of a Kelvin of energy, so at ordinary temperatures the field is already crowded with random microwave quanta and any entanglement would drown instantly. At millikelvin, the thermal occupancy of each mode falls essentially to zero, and the only fluctuations left are the irreducible quantum ones you can shape, correlate, and, in the right combinations, suppress below the vacuum level in one joint variable while paying the price in its partner. Exactly the trade that lets two distant beams act like one carefully choreographed instrument. What can you do with these class microwaves besides admire them? First, you can entangle qubits that never touch. A superconducting qubit on chip A is coupled to a resonator that releases a microwave photon whose properties encode the qubit's state. On chip B, another resonator greedily absorbs only that matching photon. By arranging the emission and absorption to be indistinguishable and by measuring a suitable joint signal, you herald a bell pair between the two qubits, even though the only thing that traveled was a fragile microwave. The tighter and cleaner your squeezed twin beams, the more efficient these remote links become, laying groundwork for modular quantum processors in which separate cryostats or chips swap entanglement like letters down a low-loss coax. Second, you can read qubits faster and softer. Feed a carefully oriented squeeze state into the readout resonator and the quadrature carrying information about the qubit state arrives at your amplifier with less noise than vacuum would allow, which lets you shorten the measurement, or reduce the measurement power without giving up confidence. This is not hand-waving experiments. Plot histograms of readout outcomes with and without squeezing, and show the clouds separating more cleanly. Along the decision axis while spreading harmlessly along the orthogonal one, a geometric picture of how engineered noise buys you speed. Third, you can push sensing into murky bands, because many technologies, from biology to radar, live in the microwave domain. There is appeal in detection schemes that retain an advantage even in bright backgrounds. Protocols inspired by quantum illumination use one of the entangled partners as a probe and keep the other as a reference, then perform a joint measurement that can eke out a few precious decibels of advantage in distinguishing target present from target absent, even when the return is swamped by thermal photons. The advantage is modest and conditional, but it survives in regimes where naive quantum tricks fail, showing that correlations can be useful even when entanglement per se is technically broken by the environment. A fourth, more architectural payoff is microwave networking with security features rooted in physics. You can certify that a stream of joint quadrature data couldn't have been pre-written by classical noise sources using inequalities tailored to continuous variables. Then run key agreement protocols that harvest secret bits from the shared randomness. Here, the same measurements you use to map the covariance matrix double as health checks for the link, catching drift or tampering as a rise in noise or a tilt in the squeezing ellipse. None of this comes free, and the limits teach you what is being juggled. Every connector and cable adds loss that dilutes the correlations. Ferrite-based circulators are bulky and warm, so integrating their function on-chip with parametric directional amplifiers and non-reciprocal metamaterials is an active race. Pumps can leak and create spurious tones that mask the very signals you care about. And long-distance distribution is hard because microwaves absorb in air and pick up room temperature noise quickly. So serious networking over kilometers will demand transducers that convert entangled microwaves into entangled light and back with high efficiency. And low added noise, a tall order researchers are attacking, with vibrating membranes that talk to both photons and phonons, with piezoelectric bridges on silicon, and with electro-optic crystals that promise clean translation if you keep parasitic modes in check. Verification, too, is a discipline rather than a slogan. You never declare entangled after one pretty trace. You reconstruct the full covariance matrix from many quadrature settings. You apply trusted criteria that flag non-classicality without assuming ideal detectors. You compare the measured squeezing against an independently calibrated vacuum reference. And you track stability over hours, because useful machines cannot live on heroic snapshots. When the numbers hold, when the inferred logarithmic negativity stays positive under reasonable error bars, when the joint noise dips below vacuum by repeatable margins, when the two-mode interference fringes remain high contrast as you sweep phases, you can say with a straight face that you're not just making quieter microwaves, you're making correlated quiet that mechanics alone cannot fake. If you step back from the fridge and look for the idea that will still matter when today's acronyms are obsolete, it is this: in the microwave world, where thermal noise is normally a bully, structure plus cold plus nonlinearity let you reshape randomness itself, steering fluctuations into patterns that cooperate across distance, turning amplifiers that once merely made signals louder into instruments that make meaning cleaner, and enabling qubits, sensors, and links to perform above the floor that uncorrelated noise would impose. And the gentlest human lesson hidden in those corrugated aluminum boxes is that clarity doesn't always come from raising the volume. It comes from holding two things together so that what shakes one steadies the other. Two quiet hands on the same steering wheel, guiding a signal through a noisy world, not by force, but by balance. Bose-Einstein, condensates with phase tricks. You don't usually think of drawing on a gas with something as intangible as phase, yet that is exactly what physicists do with Bose-Einstein condensates. They cool a cloud of atoms until thousands or millions of them settle into a single, shared wave, and then they write invisible patterns into that wavefront, so the atoms flow, twist, and knot in ways ordinary matter never could, turning a smear of ultra-cold vapor into a controllable playground where the pen is light, the ink is phase, and the picture appears only when the atoms respond. The starting point is simple to say, and hard to achieve. Trap a dilute gas in magnetic or optical fields and remove energy until its temperature falls to billionths of a degree above absolute zero, at which point the atoms stop behaving like little marbles and begin acting like one collective matter wave with a well-defined rhythm across the whole cloud. And that rhythm, the condensates phase, becomes the steering wheel for everything that follows. With a condensate in hand, the first phase trick is also the most revealing. Split it into two pieces, let them drift apart a bit, then switch off the trap and allow the expanding blobs to overlap. Where the peaks of their internal waves agree, you get bright bands of high density. Where they oppose, you get dark lanes. And the spacing and bending of those fringes tell you directly how the phases differed from place to place. If a vortex was hiding in one cloud, the interference shows a little forked dislocation like a torn zipper. If a smooth gradient was present, the stripes tilt like a slanted barcode. This readout by overlap is how people learned that condensates really do carry a single coherent phase across distances that would dissolve order in a normal gas. The second trick is to imprint a chosen phase rather than just read it. Shine a brief, far-off resonant laser pattern through the cloud so it shifts the atom's energy by a hair for a few microseconds. That tiny, controlled delay becomes a step in the phase where the light touched. And when the light turns off, the atoms react to the new internal map you've drawn. One sharp phase step launches a dark soliton, a moving notch of low density with a distinctive knife-edge profile. A radial ring pattern launches soliton trains that ripple inwards and outwards. A spiral imprint in a toroidal trap winds the phase around the ring, and because the total twist must be an integer, multiple of a full turn, the gas develops a persistent current that runs indefinitely, like a tiny, frictionless river. If you stir the condensate gently with a focused laser spoon, or rotate the trap itself, another phase story appears. Above a certain speed, the flow cannot remain smooth, and a vortex pops in, a topological whirl with exactly one quantum of circulation and a clear, empty core. Arrange the stirring cleverly, and you can paint whole lattices of vortices that pin down an effective magnetic field felt by neutral atoms. And if you dial in synthetic gauge fields using Raman lasers, you can create spin-orbit coupled condensates where the phase of one internal spin texture locks to the motion. Seeding patterns, stripes, Skyrian-like swirls that classical fluids do not know how to make. On the scale of two nearby condensate wells linked by a narrow channel, phase becomes a busy traffic officer. A small difference drives Josephson oscillations in which atoms slosh back and forth at a frequency set by the link and interactions. Push the phase bias further, and the traffic jams into self-trapping, with atoms preferring one side while the phase winds steadily. Wrap that link into a ring, and you've built an atom squid, sensitive to rotation through the Banach effect, because a tiny twist of the lab shifts the phase that atoms accumulate as they flow around the loop, changing how easily they pass the weak link. Suddenly, your ghostly phase makes a very practical gyroscope. Phase also narrates how order is born. If you cool too fast across the transition into condensation, far apart regions choose their initial phases independently and can't reconcile them in time, so they stitch together with seams, vortices and defects, whose number reflects how abruptly you crossed, a chilly echo of the Kibble-Zurek idea that rapid symmetry breaking breeds topological scars. Slow the cooling and the phase field heals more completely, leaving a cleaner, calmer condensate. Interactions let you complicate the palette still further. Use a magnetic field to tune the way atoms push on each other, a Feshbach resonance, and the same phase imprint that made a dark notch in a repulsive. Gas will instead call up a bright soliton in an attractive one, a self-focused hump that travels without spreading like a pearl on silk. Confine motion to a skinny channel, and strongly repulsive atoms line up into a Tonks-Girardeau gas, where they avoid each other so thoroughly that the many-body phase echoes a system of impenetrable particles, even though the atoms still carry waves. Spread the cloud flat, and you meet a two-dimensional world where long-range order is delicate and BKT physics takes over. The phase can remain locally stiff, yet give way to vortex-anti-vortex unbinding at a characteristic temperature. A vivid lesson in how dimensionality decides what order really means. Every one of these tricks demands honest bookkeeping about noise. The larger the phase pattern you write, the more it invites the environment to eavesdrop through stray fields, vibrations, or warm radiation. Phase diffusion slowly blurs a condensate's rhythm when atom number isn't perfectly fixed. Imperfect light pulses tug the phase unevenly, so your intended soliton frays into sound. Barriers that drift by nanometers change Josephson frequencies enough to smear the clean oscillations you wanted. So groups fight back with better vacuum, lower temperatures, quieter current supplies, and feedback that nudges the phase back into place by watching the interference in real time. The payoffs go beyond pretty pictures. Matter wave interferometers based on condensates can measure gravity, gradients and rotations with high stability, because the phase accumulates predictably along different paths. Atomtronic circuits, rings, junctions, and lattices designed not for electrons but for neutral atoms offer a way to prototype elements of future quantum technologies where current is a superfluid flow and memory is stored in quantized phase windings. And phase engineering has become a broadly useful diagnostic, a way to ask, what does the condensate know here, without smashing it with strong probes? Perhaps the most surprising lesson is philosophical rather than technical. You discover that phase is the gentle currency of control, a way to steer without shoving, to encode motion and memory without carving tracks in a surface. With Bose-Einstein condensates, you learn to guide by timing and to measure by listening for rhythms. And the closest analog outside the lab is learning a song rather than building a machine. Once the melody is carried by every voice in the choir, a single well-placed pause or a subtle change of key reshapes the whole piece. Inside the refrigerator cold chamber, that pause is a phase step, that key change a twist around a ring. And when the trap lights dim and the overlapping clouds finally reveal their stripes, you see that calm structure emerge not from force, but from coherence. A reminder that sometimes the clearest pictures are those you draw where everything moves together, and a whisper in the right place can set the pattern for everything else. Quantum walks on optical lattices. You step into a room where the light itself makes a chessboard, and you're invited to watch a traveler that follows rules your instincts don't expect. A quantum walk on an optical lattice, where a single ultra-cold atom or a faint packet of light doesn't meander like a drunk pedestrian, but surges outward in a deliberate, wave-guided bloom, carrying information about the landscape in the way its probability fans and folds. The board is built by crossing laser beams, so their standing waves form a crystal of light, a grid of wells that can hold atoms one site at a time, and the walker begins pinned to a spot, prepared gently so its internal state, often two stable levels you can address like heads and tails, acts as a coin that decides direction. In the discrete time version, you tick the experiment like a clock, flip the quantum coin with a short pulse, then shift the atom left if it's in one coin state and right if it's in the other, using state-dependent forces from polarized light, because the coin was set in a superposition. The walker doesn't choose left or right, it advances in both, and after a few steps the distribution is no longer a bell-shaped smear, but a pair of sharp lobes racing away from the origin, a hallmark of interference that makes the spread ballistic rather than diffusive. In the continuous time flavor, you skip the coin and simply allow tunneling between neighboring wells to happen all the time, and the same wave logic appears in the way the amplitude ripples across the grid, revealing symmetries and bottlenecks of the lattice without ever drawing a line on paper. What makes this more than a pretty diffusion movie is how sensitively the walker records the rules you write into the board. Tilt the lattice slightly, and one lobe strengthens while the other fades. Add gentle disorder, tiny, random shifts in site energy, and the outward surge can localize, stalling near the start in a way that captures the famous balance between coherence and randomness known from disordered solids. Modulate the coin in a pattern that alternates every step, so-called split-step walks, and you craft topological phases where the bulk of the lattice looks inert, but the edges carry robust, directed motion that shrugs off small defects. These edge paths are not decorations, but guaranteed by the way your coin and shift are sequenced, and you can watch the walker hug the boundary even as you roughen the interior. A tangible lesson in how global structure protects local behavior. The lab tools that make this concrete are quietly beautiful. Optical lattices with adjustable depth set the tunneling rate. State-dependent lattices or microwave gradients implement the conditional shift. Quantum gas microscopes image single atoms with site-level resolution, so you can read out the full probability map after each number of steps. And single-site addressing lets you paint patterns, barriers, defects, or phase twists directly onto the grid to see how the walk adapts. With these, you can benchmark the difference between a classical random walk, where variance grows linearly with steps, and the quantum version, where variance grows quadratically by simply plotting how fast the distribution's width expands. No equations needed, just dots on a camera that move too quickly to be ordinary chance. Once you accept the walk as a programmable playground, it becomes a pocket-sized simulator. Choose a coin protocol that mimics spin-orbit coupling, and the dispersion of the walker mirrors that of particles in exotic materials. Stitch multiple sub-lattices, and you reproduce Dirac-like cones where motion is eased in some directions and slowed in others. Add periodic driving, and you create flocate walks whose effective rules emerge only over many steps, with phases that cannot exist in static systems. Sprinkle a controlled weak measurement, pausing to ask, "Are you here?" with a faint, lossy probe, and you watch how interrogation itself reshapes motion, sometimes freezing it, a hint of the Zeno effect, sometimes guiding it like a soft hand on the back. Though optical lattices with atoms are a natural host, photonic platforms run the same playbook with waveguides carved into glass. A single photon is split across channels, the coin is implemented by directional couplers, and the shift is the physical routing of paths within the chip. There, the advantage is permanence and scalability, many steps on a footprint smaller than your palm, while the cost is reduced reconfigurability compared to moving atoms with light. In superconducting circuits, microwave pulses through networks of tunable resonators enact yet another version, proving the walk is a framework rather than a single machine. These walks are not just toys. They sharpen sensors and algorithms in ways that are easy to test. Encode a search problem into a marked site whose energy is shifted, and the quantum walker finds it faster than a classical browser would, the speed up visible in how quickly the probability peak settles over the target. Map a gradient field, magnetic, electric, or gravitational, into a gentle tilt, and the walker's asymmetry becomes a meter for that tilt, with sensitivity set by how many coherent steps you can keep. Use edge channel robustness to route atoms around defects, and you have a blueprint for disorder-tolerant atomtronic circuits. Fold interactions into the mix, letting two walkers meet and briefly bind, and the walk explores chemistry-like reactions in slow motion, with bound pairs spreading differently from singles, revealing how pairing changes transport. The honest limits arrive from the same place the magic does: coherence. Every step must preserve phase well enough that the left-moving and right-moving histories remain capable of interfering when they reunite. Stray light, imperfect polarization, and finite temperature slowly wash that memory away, turning the ballistic surge into a muddled shuffle. To push back, you deepen the lattice during coin flips to suppress unwanted tunneling. Flatten magnetic fields so coin rotations are uniform across the grid. Filter laser noise so phase remains stable across dozens of steps. And sometimes echo errors by reversing operations in mid-walk to cancel drifts. When the maintenance works, you watch visibility, contrast in the interference fringes embedded in the distribution. Hold steady long enough to claim behavior beyond any plausible classical mimic. If you want a simple sanity check that does not lean on jargon, it is this. After a fixed number of steps, a classical Walker's arrival histogram is tallest at the center. The quantum Walker's is hollowed out there and lifted at the wings, as though decisiveness replaced dithering. Move a single defect one site to the left, and the entire pattern shifts in a way that contains a fingerprint of that move. Put 2 Walkers in and tag them with internal labels. Then see whether they avoid or bunch. Their correlation map whispers whether interactions or indistinguishability are at play, each leaving a different geometric signature. Beneath the instruments lies a softer lesson worth carrying. A quantum walk is motion under coherent possibility, an exploration where going both ways now makes later clarity sharper, not fuzzier. It shows that randomness need not be wasteful if structure is present, that speed can come from keeping options alive rather than pruning them early, and that landscapes reveal themselves most cleanly when you let the traveler be more wave than point, and when the run ends and the lattice lights fade. You're left with a quiet thought that stretches beyond physics, that there are times in life when spreading with intention, allowing parallel tries to inform one another before you choose, turns stumbling into mapping, and that the patterns you make by walking that way record truths about the terrain no single path could have taught you. Optical lattices, simulating exotic matter. You're told you can build a material without mining a single rock, and at first it sounds like a metaphor, but then you watch a room full of laser beams weave a crystal of light and you realize that, inside their crossings, atoms can be persuaded to behave like electrons in worlds that nature rarely permits. Optical lattices are that craft, standing waves forming egg carton landscapes where ultra-cold atoms settle site by site. And the adventure is not just trapping them, but dialing every rule they live by, so you can ask clean questions about exotic matter and get clean answers without the impurities, vibrations, and uncontrollable quirks of real solids. Start with the simplest promise. By adjusting the lattice depth you set, how easily atoms tunnel between neighboring wells, and by changing the interactions you set, how hard it is for 2 to share a site. That's the core of the Hubbard idea. And with bosons, you can watch the smooth flow of a superfluid freeze into a Mott insulator as you deepen the wells. Coherent matter turning into an orderly array with 1 atom per site. Not because something broke, but because repulsion outweighed the urge to move. Switch to fermions, and you walk into the territory that keeps condensed matter theorists awake. The Fermi-Hubbard landscape that underlies magnetism and, many suspect, unconventional superconductivity. In the lattice you can tune density precisely, cool patiently, and then look directly for patterns. Staggered alignments that signal anti-ferromagnetism at half filling, hints of stripes and correlated motion when you dope away from that point, and short-range pair tendencies that would be murky in a real crystal, but appear here in carefully averaged snapshots. Those snapshots are literal. Quantum gas microscopes resolve single atoms, letting you take images that show where each particle sits and how neighboring spins correlate. By repeating the experiment many times, you build a statistical picture of order emerging from noise, and you can even freeze the dynamics midstream with rapid lattice ramps to catch how correlations grow after a sudden change. Like pausing a movie to study the frame where the plot turns. With the geometry under your hands, you're not limited to square grids. By interfering beams at new angles, you conjure triangles, honeycombs, and kagome patterns, each with its own flavor of frustration, the kind that prevents simple magnetic order and makes the ground state a subtle act of balance. These geometries matter because they host flat bands where motion is sluggish and interactions dominate, or Dirac-like cones where motion is agile and chiral, and they open doors to phases that are more delicate in ordinary materials, from spin liquids that resist freezing to charge orders that live alongside mobility. To make the atoms feel magnetism without carrying charge, you imprint phases on their tunneling using laser-assisted hops or periodic shaking, and suddenly atoms moving around a plaquette act as if a magnetic field threads the loop. In this regime, you can map out patterns of energy that form fractal butterflies when you vary the effective flux, or realize topological bands where the bulk stays quiet, but the edges carry robust flow that resists roughness. Run a slow, cyclic change of parameters, and the cloud shifts by an exact number of lattice sites each cycle. a quantized pump that serves as a clean demonstration of protected transport without fragile wires. If you crave richer internal structure, alkaline earth atoms offer a gift. Their nuclear spins barely talk to the light, so you get many spin flavors that interact almost equally, creating a playground for large symmetry magnetism, where the rules of alignment differ from familiar two-state systems. By preparing balanced mixtures and letting them evolve, you can test how quickly and in what patterns such complex spins order, and whether cooling by rearrangement, a trick borrowed from classic thermodynamics where order absorbs heat, can help you reach the stubbornly low entropies needed for the most coveted phases. Long-range forces write another chapter, with strongly magnetic species like dysprosium or erbium, or by dressing atoms with off-resonant light to mix in a hint of longer reach. You move beyond only neighbors talk to interactions that stretch across several sites. Then density waves, supersolids, and charge orders compete and cooperate. And by nudging parameters, you watch one pattern give way to another, a living phase diagram laid bare on a camera sensor. Exotic does not have to mean static. Gentle shaking of the lattice, changing its parameters in time, creates effective Hamiltonians that would be awkward to realize otherwise, letting you flip the sign of tunneling, flatten bands, or generate synthetic spin-orbit couplings that tie an atom's internal state to its direction of motion. Under these drives, you can prepare phases that have no counterpart in stationary systems, then switch the shaking off and see which features persist and which evaporate, a way to probe how robust your engineered matter really is. Probing itself is a careful art. Time-of-flight expansions translate momentum distributions into real space images. Bragg spectroscopy measures how the system absorbs a gently shaken lattice, revealing collective modes that differentiate superfluids from insulators and magnetically ordered states from disordered ones. Noise correlations, subtle patterns in the shot-to-shot fluctuations, act like fingerprints of pairing or hidden order, and pump probe sequences watch how a small, localized poke sends waves through the system, timing their travel to infer stiffness and damping, like a doctor with a stethoscope. None of this is effortless, and the limits teach you why these platforms are impressive. The temperatures and entropies at which the most interesting orders bloom are tiny compared with everyday scales. So every scattering event, every stray heating mechanism, and every imperfection in the lattice alignment matters. Teams counter with deeper traps that isolate motion, sympathetic cooling, where some atoms play refrigerator for others, and meticulous stabilization of laser phases, so the synthetic gauge fields and engineered couplings don't drift. Verification is not left to faith. Claims of order are checked by multiple, independent signatures, images of staggered spin patterns, spectroscopic gaps that match theory, transport responses that flip sign when you invert the synthetic field, and by varying control knobs one at a time to see whether predicted thresholds and critical points fall where they should. When different probes agree, you trade beautiful pictures for solid evidence. The payoffs are twofold. Practically, these simulators benchmark theories that are otherwise stuck between crude limits and heavy numerics, giving concrete data where the math alone wanders. Conceptually, they show that material is a set of rules more than a set of atoms, and that by writing those rules with light, you can build worlds where the essentials are highlighted and the distractions removed. The most helpful realization, once the lasers go quiet and the atoms are released, is gentle rather than grand. Exotic matter is not an occult substance. It is a conversation between motion, interaction, and symmetry. And optical lattices are a way to moderate that conversation so each voice can be heard. You learn that patterns you thought were inaccessible are simply shy. That clarity comes from tuning rather than force. And that by crafting a clean stage, a crystal of light with honest, adjustable props, you can watch order emerge, compete, and transform in real time. Walking away not with a myth, but with a map of how complexity grows from simple rules when you give it the space and the stillness it needs. Loophole-free steering demonstrations. You can tell a field has matured when it can prove a claim even while treating half of its own apparatus as untrusted, and that's the peculiar grace of loophole-free steering. An experiment where one party's device may as well be a sealed box with flashing lights, yet the other party can still certify without peeking inside. that the shared system really is entangled, and that the black box side could not have faked the correlations with any pre-written script. The core idea is older than it sounds. Einstein once worried that by choosing what to measure on her particle, Alice could steer the state of Bob's distant particle. But the modern version turns that discomfort into a testable promise with clear rules, and the laboratory version turns those rules into hardware, timing and bookkeeping that leave no ordinary escape routes. Here is the shape of a clean demonstration. Start with a bright, high-purity source that creates pairs of entangled systems, often photons from a non-linear crystal or two beams of squeezed light, and send one member of each pair to Alice and the other to Bob. Bob's station is the trusted side, so he calibrates his measurement axes and efficiencies in advance and keeps them stable, while Alice is treated as a black box that accepts a question and outputs an answer. For each trial, Bob picks a setting at the last instant using a high-speed random generator, measures his particle, and records the raw result even if the detector stays silent. Alice also receives a setting and returns an outcome, but crucially, Bob never throws away trials for which Alice didn't respond, or for which his detector misfires. There is no fair sampling assumption to massage the data, and when the run ends, Bob groups his own results by the announced settings and outcomes from Alice and asks a simple but powerful question. Could all of these grouped data have come from an ordinary local hidden state model in which Alice's device spits out answers from a private list, while Bob's particle was never entangled to begin with? The steering inequalities you read about in papers are just the tidy, testable versions of that question. Violate them by a comfortable margin with honest error bars, and you have certification that Alice really influenced which states Bob's data are compatible with, not by sending a signal during the trial, but by sharing entanglement at the start. Calling it loophole-free means particular doors are bolted. First, the detection door. Steering is more tolerant of loss than Bell tests. But a determined classical strategy can still hide in missed events, so the total efficiency, source, optics, detectors must be high enough that the observed violation cannot be blamed on selective reporting. Experiments get there with low-loss optics, superconducting nanowire detectors that turn single photons into crisp electrical blips, or, with continuous variables, homodyne receivers that read quadratures with near-unit efficiency. They also record no-click outcomes explicitly, so that every heralded pair contributes to the statistics. Second, the communication door. Even though steering is one-sided device independent, you still have to make sure Alice's output could not have been tailored by learning Bob's choice in time, so setting choices are made fast and independently. Stations are separated enough that a light-speed signal can't cross in time, and electronics are shielded, so the only thing shared between rooms is the original entangled state. Third, the freedom of choice door. The random bits that pick Bob's measurement are drawn from a source with no plausible ties to the entanglement source or to Alice's box. Phase noise, photon arrival times, or even distant astronomical light. A belt and suspenders step that starves any common cause explanation. Fourth, the memory door. Clever black boxes might adapt over rounds, so analyses avoid assuming independent, identically distributed trials, and instead use finite data methods that remain valid with drift and autocorrelations. Along the way, calibration of the trusted side is cross-checked before and after the run, so the trust itself is earned and documented rather than assumed. Underneath the headlines, the setups are tangible. Polarization entanglement over fiber spools with fast electro-optic modulators that flip Bob's basis in microseconds. Time bin pairs where Bob's unbalanced interferometer is phase-locked for hours so long-term drift doesn't fake a pattern. Continuous variable pairs where twin beams are measured with homodyne detectors whose phases are swept to sample many directions in phase space. In each case, the lab logs include every trial's timestamp, setting, and outcome, and the analysis never cherry-picks windows or rejects bad rounds after the fact. Why do all this when Bell tests already exist? Because steering fills a different niche in the hierarchy of quantum weirdness, and a different niche in applications. It sits between simple entanglement witnessing and Bell non-locality, and that middle ground is exactly what you want for one-sided device-independent tasks. Cryptography, where only the receiver's measurement device is trusted. Cloud-style entanglement verification, where a user tests a remote provider without inspecting their hardware. Certification of measurement incompatibility on the black box side. And quality control for teleportation and remote state preparation claims, where you want the guarantee to stand, even if the sender's gear is a mystery. The signatures are easy to recognize once you know what to look for. Bob's conditional states, the ensembles you get when you slice his data by Alice's declared outcome, become too tight, too aligned to have come from any pre-assigned local list. Plot them as little ellipsoids on a block sphere, or as patches in phase space, and they cluster in a way that no classical shadow can mimic. Turn the knobs to weaken entanglement or increase loss, and those clusters spread until the violation disappears right where theory says it should. A sanity check that the effect isn't a mirage. The same discipline exposes the cracks you have to mind. Stray reflections can leak basis information between stations. Unequal detector efficiencies can bias the conditional states if not carefully included in the model. Instability in the trusted side's axes shrinks the violation over long runs, and timing skew can bias which trials are matched if you define coincidences carelessly. None of these issues are mysterious, but they only stay tamed with vigilant stabilization, optical hygiene, and pre-registered analysis plans that make moving the goalposts impossible. The payoffs reach beyond philosophy. In networks, a small organization can buy or rent an entanglement source and still verify it remotely without trusting the vendor's settings. In sensing, steering inequalities double as health checks for measurement incompatibility, telling you whether your instruments genuinely access non-commuting observables or have drifted into a friendly classical regime. In security, one-sided protocols turn steering violations into secret bits with guarantees that survive malicious gear on the transmitting end. A realistic threat model for distributed systems where not every node belongs to you. The human lesson is the same one you've been collecting through this series, but cast in a new light. Certainty worth having does not always come from transparency. It can come from structure, from choosing a test whose very shape denies cheaters room to maneuver. Loophole-free steering thrives on that discipline, on the insistence that every trial counts, that independence is enforced by space-time itself, and that claims are tied to inequalities whose violation is plain in the numbers. And when the run is over and the histograms have settled, you don't walk away muttering about mystical influence at a distance. You walk away with something calmer and more useful, a proof that even with one black box in the room, reality lets you rule out all the easy ways to fake quantum behavior. And a reminder that trust earned by constraints can be stronger than trust offered by inspection. Teleportation over fiber and free space. You hear the word teleportation, and your mind leaps to vanished bodies and sudden arrivals. But what the lab actually delivers is subtler and more useful. A way to move the shape of a quantum state from here to there without the particle ever crossing the gap, by arranging 3 threads, shared entanglement, a joint measurement at the sender, and an ordinary message racing along a classical line. And when those threads are braided tightly enough across fiber and free space, the receiver's system is driven on demand into a faithful copy of what the sender held a moment ago. No mass moved, no cheating with faster-than-light whispers, just a choreography that turns correlations into a courier. The routine starts long before the big moment. An entangled pair is created at a convenient wavelength, telecom bands if you're aiming for buried fiber, a visible or near-infrared color if you're going through air, and the partners are sent to 2 distant stations you'll call Alice and Bob. Meanwhile, a third photon, or an atom, or a spin in a solid carries the fragile state you want to transfer. At Alice's node, a special joint measurement compares the unknown traveler with her half of the pair. In everyday language, she asks, "How does this state sit relative to my share of the correlations?" And the only way to learn that particular relational fact is to project the 2 particles into one of a small set of entangled outcomes that erase any separate identity either one had before. By itself, that measurement scrambles the traveler's local record. But it also writes a simple 2-bit instruction that tells Bob exactly which small twist he must apply to his remote particle to shape it into the state Alice lost. Those 2 bits are sent over the regular internet, a radio link, or a cable, and as soon as Bob receives them, he performs the corresponding correction and, if the channels were kind, holds in his lab a system that behaves under any test you could perform, like Alice's original. The beauty and the pain live in the channels. In fiber, the opening moves look calm. Glass quietly guides light through cities and under oceans. And if you choose the right wavelength, the loss per kilometer is small enough that a few tens of kilometers feel routine. Yet small is relentless. Attenuation compounds, scattering makes clicks sparse, and splices and bends nibble away at your budget. So successful field teleportation over fiber uses tricks that sound like common sense and are, in fact, hard-won engineering. Encode information in time-bin qubits whose early-late rhythm survives long runs better than delicate polarization. Stabilize fiber length with pilot tones so that phases don't drift while your detectors wait. Convert awkward source wavelengths to telecom bands with nonlinear crystals so you can mingle with existing infrastructure. And rely on cryogenic single-photon detectors whose dark counts are low enough that a real signal can be believed. Because the 2-bit instruction must arrive in time for Bob's correction, networks include fast classical side channels or a fiber strand allocated to timing and control. Because stray temperature changes stretch fiber by enough to shift phases, the control layer constantly nudges the interferometers back into alignment. Because cities are noisy, field systems timestamp everything and use stringent coincidence windows so that a click in one district is paired only with its true partner across town. Free space is loud in a different way. The air above a city or a desert throws your beam around with turbulence. Sunlight floods your detectors with stray photons. And the Earth's curvature laughs at any plan that involves a straight line across a continent. Yet in the right conditions, clear night skies, high-altitude paths, adaptive optics that reshape the beam in real time, spatial filters that accept only a tight core of the arriving light, you can push single-photon links across mountains or up to satellites where the thin atmosphere and long vistas trade weather headaches for astonishing reach. Here, polarization becomes attractive again because space doesn't twist it the way glass sometimes does. Pointing and tracking systems lock telescopes together with beacon lasers and fast steering mirrors. Narrowband filters and temporal gating carve signal from glare, and GPS-disciplined clocks let distant stations agree on which nanoseconds matter. The moment you bring a satellite into the story, the geometry flips from stubborn to generous. Most of the path is through near vacuum, so the beam stays tight over thousands of kilometers, and a single spacecraft can serve far-flung ground stations, allowing teleportation between places that no fiber link could connect economically. The price is orbital mechanics, brief windows, moving targets, Doppler shifts, and the need for space-qualified sources and detectors that shrug off temperature swings and radiation. But teams have already shown that entanglement and the joint measurements survive that ride, and that a 2-bit radio whisper can close the loop even while the satellite races across the sky. In both media, the fidelity of the teleported state becomes your conscience. Imperfections in the source, imbalance in the measurement, drift in the channel, and noise in detectors all pull the copy away from the original. That's why serious demonstrations report not a press-ready "it worked," but a number with error bars, and why they deliberately stress the link, adding loss, misaligning phases, or inserting known disturbances to prove that the system fails exactly where theory predicts and nowhere earlier. The honest constraints also teach you why teleportation matters beyond the headline. You cannot amplify an unknown quantum state the way you boost a radio signal, so long-distance quantum networks will need repeaters built from teleportation steps chained together with memories that hold entanglement until the classical messages arrive. Field tests already combine modest quantum memories with metropolitan fiber to show that you can store a qubit long enough to coordinate a correction, and satellite trials hint at continent-scale legs that could one day stitch together into intercontinental routes. Meanwhile, the same toolkit feeds quieter tasks. Moving a state from a chip where it was created to a chip where logic gates are more mature, handing a qubit from a delicate sensor to a robust memory without reading it, or verifying that a remote node really received what you prepared without trusting its internals. Each is a small, concrete win that leans on the same 3-thread braid. If you need a moral that sits comfortably in the everyday, it's this. Nothing spooky happens that you can exploit for instant messages, and nothing magical happens that saves you from building clean hardware. Teleportation is a pact, not a trick. The pact says that if you invest in correlations before you need them, if you measure in a way that trades certainty here for certainty there, and if you carry a modest classical message alongside your fragile quantum one, then distance stops being a wall for states that cannot be copied or peeked at. And when the last correction pulse flips at the far node, and a fragile pattern reappears, perfectly alive, in a place the original never visited, you feel a kind of calm that isn't about spectacle at all. It's about reliability, the sense that careful preparation, disciplined timing, and respect for limits can move the most delicate kind of information through fiber, through air, and, one day, through a global web where the fastest thing isn't a rumor but a promise kept by design, satellite QKD, and intercontinental keys. You look up at an ordinary night sky, and it's easy to imagine secrets getting lost in all that darkness. Yet the sober truth is that satellites can turn that darkness into a delivery route for perfectly fresh encryption keys shared between continents, an arrangement called satellite, quantum key distribution, and once you understand the moving parts, the idea feels less like a stunt and more like engineering guided by careful physics. You create fragile quantum signals aboard a spacecraft, guide them through thin air to widely separated ground stations, and use the patterns of clicks they trigger. After sifting, error correction, and privacy amplification, to distill matching keys that no eavesdropper could have copied without leaving scars in the statistics. The core promise isn't to beam messages directly, it's to distribute randomness with guarantees. The spacecraft either sends very faint laser pulses, whose intensity is deliberately varied so that any interception reveals itself, or it shares pairs of entangled photons so that two ground stations see perfectly linked but individually random outcomes. Both methods live or die by link budgets. How many genuine single-photon events survive pointing jitter, beam spreading, atmospheric turbulence, and detector noise, so the practical playbook is surprisingly down to earth. Put the source on a low Earth orbit satellite to keep paths short during each pass. Choose a downlink, so most turbulence is encountered near the receiver rather than along the whole route. Use telescopes with tight fields of view and narrow spectral filters to reject background light, and run a fast pointing acquisition tracking loop that keeps the beam on target while the spacecraft screams across the sky. On the ground, you don't decode a message. You time tag arrivals against a shared clock, compare a small public slice to estimate the error rate, and if that rate stays below a threshold, you proceed. You reconcile mismatch bits without revealing the key, then compress the reconciled strings just enough to erase any partial knowledge a spy could have gained. And what remains, provably, behaves like fresh coin flips that only the two of you hold. This is not magic but accounting. And modern security proofs are composable, meaning the key is safe to use as a one-time pad, or to seed standard ciphers without subtle leaks creeping in. Intercontinental reach comes from simple geography and some choreography. A single satellite can talk to Station A while it passes overhead at dawn, then talk to Station B half an orbit later at dusk, giving each station a private key with the spacecraft. If the satellite is a trusted node, it can combine those strings and forward one tiny piece of classical information, so A and B derive a common intercontinental key, even though they never saw the same photons. The trust label matters. If you treat the spacecraft as honest, this scales well today, but teams also pursue entanglement-based links where both ground stations receive partner photons from the satellite at the same time and build their key by comparing bases later. In that variant, the satellite need not be trusted to keep secrets, but the double downlink is punishing on loss, so you pay in lower rates and harsher engineering. Because the world is bright by day and fickle by weather, field systems work with what nature gives them. Night passes deliver the cleanest keys. Twilight can still work with aggressive filtering. Daylight has been demonstrated in specialized setups using tight spectral windows, time gating, and spatial filtering. But background counts push rates down. Clouds are showstoppers, so networks deploy several ground sites spread over hundreds of kilometers, letting handoffs and store and forward strategies ride out local weather. Behind the clean diagrams lurk real-world details you can't ignore. A quantum link still needs a classical authenticated channel so the public Sifting can't be spoofed. Today, that authentication is done with a small, pre-shared secret, or with digital signatures built from post-quantum mathematics. Detectors must be shielded against blinding tricks that force them to click on command. Random number generators at the stations must be demonstrably physical and fast. And finite key effects matter because a satellite pass yields only so many detection events before the spacecraft drops below the horizon, so you estimate secrecy with honest margins rather than wishful asymptotics. Even the optics reads like a checklist. Adaptive mirrors can pre-compensate beam distortions. Star tracker updates feed the pointing loop. Polarization states must be calibrated on the fly, so the atmosphere or glass doesn't skew measurement bases. And frequency converters sometimes translate sturdy onboard sources to telecom wavelengths, so existing fiber backbones can ferry the classical side channel and route finish keys to data centers. What do you actually do with an intercontinental quantum key once you have it? The quiet, practical answer is you blend it into normal security stacks. Use it to refresh symmetric keys more often than you could with slow manual exchanges. Feed it to one-time pad boxes for diplomatic or critical control traffic when bandwidth is modest. Escrow keys across multiple geographically diverse ground stations, so no single weather event or hardware failure blocks delivery. And integrate health metrics from each pass. Losses, error rates, estimated information leakage into dashboards that decide whether a key is accepted, shortened, or discarded. It's also worth noticing what satellite QKD is not. It doesn't make the internet unhackable. It doesn't replace careful software practices, and it doesn't eliminate the need for cryptography based on hard math. Instead, it adds a new source of trust anchored in physics. If someone tries to copy your quantum carriers, the error rate climbs and the session is thrown away. And that complements, rather than competes with, crypto systems designed to resist advances in classical and quantum computing. The hardest questions are philosophical only on the surface and deeply operational underneath. Do you trust spacecraft you don't own, or do you limit yourself to entanglement links that deny the satellite any knowledge of the bits? Do you accept lower key rates in exchange for that reduced trust? Or do you insist on national or private satellites whose custody you control? Do you architect a mosaic of ground stations and orbits so keys trickle steadily across time zones? Or do you build larger memory-assisted relays so you can buffer entanglement across long gaps? And how do you fuse QKD with post-quantum algorithms so that even if one pillar cracks, the roof stays up? The deeper lesson: once you've seen a pass from horizon to horizon and watched a raw blizzard of clicks collapse into a neat, shared string is gentle. Security can be a measurement, not just a belief, an outcome protected by simple physical limits that no brand name can override. Satellites don't make secrecy effortless. They make it checkable. And when sunrise washes out the stars and the downlink shutters for the day, what's left on your server is not a trophy but a tool, a key distilled from fragility, used with discipline, and renewed the next night when the sky again turns dark and honest. Quantum repeaters. Memory-assisted entanglement. You've probably been told that distance is the natural enemy of quantum links, that photons fade in glass and air long before two far-flung labs can do anything interesting together. But the quiet revolution of quantum repeaters teaches you a different habit. You stop trying to throw a perfect state across the whole span in one heroic shot, and instead stitch a long connection from many short, well-kept promises, elementary entangled links stored in memories, verified by heralds, and fuse step by step with operations that respect the rules you can't cheat. And when you see that choreography run end to end, you understand why memory-assisted entanglement isn't a buzzword. It's the only way a quantum network grows beyond a science fair table. The basic plan is as practical as it is delicate. Divide a long route into manageable segments, build entanglement across each segment locally, and park those fragile correlations in quantum memories at the nodes until neighboring segments have succeeded. Once two adjacent links are alive at the same time, you retrieve the stored states, perform a joint measurement on the middle, station's qubits, a bell-type projection that does not reveal any private bit, and thereby swap entanglement, so the outer stations become entangled, even though no photon has traveled the full distance. Repeat this nesting: link, store, swap. Link, store, swap. until the endpoints share a usable resource. And because each step was heralded by real detector clicks, you never gamble the next operation on wishful thinking. What makes this subtle rather than straightforward is the strict budget you must balance at every node. Memories have to hold coherence long enough for their partners to succeed, milliseconds to seconds in realistic field settings. They must return the stored state on demand with high efficiency, so your hard-won pairs don't evaporate at readout. And they need multi-mode capacity, the ability to store many temporal, spectral, or spatial channels in parallel, so you can try often in the same wall clock time and beat the tyranny of probabilistic sources. Add to that an insistence on compatibility with the wavelengths that actually travel, telecom bands in fiber, well-behaved near-infrared in free space, and you see why practical repeaters lean on frequency conversion. Stages that shift light from whatever color their matter systems prefer to the color the line accepts, and back again without scrambling the quantum information. Different platforms meet these requirements in different ways that you can picture without equations. In atomic ensemble repeaters, a faint Raman pulse written into a cold or warm vapor creates, with a small probability, a single spin wave, a collective excitation spread over many atoms, heralded by a companion photon that races down the link. Two remote nodes create such excitations. Their herald photons interfere at a middle station, and a particular joint click pattern tells you the spin waves are now entangled, even though the atoms never met. Later, a read pulse retrieves each spin wave as a photon to feed the swapping measurement. And because the excitation was collective, retrieval can be efficient and directional. In rare earth-doped crystals, an atomic frequency comb acts like a built-in timer. An incoming photon is absorbed across many ions and, thanks to a comb tooth pattern in their resonances, re-emits after a programmable delay or on demand when a control field moves the excitation into a long-lived spin state in trapped ion or color center nodes. Each memory is a well-defined spin in a single particle that couples to a cavity, so an emitted photon carries its identity cleanly into the fiber, and a retrieved photon inherits it back. All of these split the same work. Generate link-level entanglement with light, store the result in matter with a long, quiet lifetime, and read it only when the network schedule says the time is right. Because no quantum state can be amplified the way you boost a radio signal, rates depend on beating loss with strategy rather than volume. Use heralding to know when to proceed. Run purification on stored pairs, simple local circuits that sacrifice two low-fidelity pairs to distill one cleaner pair, so that errors don't snowball as you nest swaps, and exploit multiplexing so dozens or hundreds of modes attempt the same job in parallel while your memories wait. With enough modes, the chance that at least one attempt succeeds during a memory's lifetime climbs sharply, turning otherwise glacial links into something that feels like a clocked service. Every layer has enemies, and they are ordinary. Fiber eats a fixed fraction of photons per kilometer. Phase drifts between independent lasers at remote nodes blur the interference that heralded links rely on. Detectors click sometimes when no photon arrived. Memories wander in frequency or leak information to their surroundings. So the countermeasures are ordinary too, but relentless. Anchor lasers to low-drift references and distribute clean pilot tones for phase stabilization. Gate detectors in narrow, trusted time bins and cool them so dark counts stay low. Shape control pulses to avoid exciting wrong transitions. Measure everything with time tags, so you can keep only events that line up in spacetime the way your protocol assumes. And design your network control like a traffic manager. Repeat until success at each segment. Retry faster than memories decay. Schedule swaps in rounds so heralds from distant segments arrive in time. And keep an honest ledger of fidelity so you decide when to purify and when to move on. As ideas mature, two philosophies of repeaters are learning to share the road. Entanglement swapping repeaters that we've been describing, which are forgiving of imperfect components but rely on heralded success and memories. And error-corrected one-way repeaters that aim to transmit blocks of qubits encoded in quantum error-correcting codes. The latter burn far more physical qubits per logical qubit, but promise steady, deterministic flow. Once hardware crosses demanding thresholds for loss and gate fidelity. In between lies an elegant third path. all photonic repeaters that replace matter memories with very large, loss-tolerant cluster states of light. So the memory is baked into the network structure. Today, matter-based approaches remain the more accessible route to long distances with modest hardware, while error-corrected and all-photonic ideas set the horizon for truly global rates. You'll notice that repeater nodes are not monolithic. Some are good at storage, some at brightness, some at interface, and practical designs mix strengths. Use a bright source to create entanglement quickly, a converter to move its color into telecom, a memory to hold it quietly, and a cavity to release it sharply on demand. Even more, field networks marry ground repeaters to satellite links, letting space handle the long lossless hops, while ground memories buffer and synchronize the pieces, a hybrid architecture where memories tame randomness and orbital passes. If you want to know whether a memory is any good without diving into jargon, 3 plain metrics help: how long it keeps a state, coherence time, how much of the stored light you get back, efficiency, and how many distinct channels it can juggle at once. High numbers on all 3 mean your repeater spends less time waiting and less time apologizing for lost or noisy pairs. Practically, teams report these alongside fidelity, how faithfully a stored and retrieved state matches the input, and they test under stress, long separations, temperature swings, and realistic link losses rather than hero conditions. The reason any of this is worth your patience goes beyond pretty diagrams. The same braid of create-store-swap that underpins a repeater lets you hand a quantum state from a sensor to a processor without reading it, synchronize distant clocks by entangling them rather than trusting unstable light paths, and move cryptographic keys that remain safe even if every device but the memories is treated as suspect. And at a deeper level, it changes how you think about distance, not as a void to cross in one dangerous leap, but as a chain of commitments you keep locally and combine with care. The soft lesson, tucked behind the cryostats and rack-mount lasers, is about pacing and structure. When something fragile cannot survive a marathon, you break the route into sprints and rest where you must. You don't demand perfection from a single throw. You demand reliable small wins and a protocol that knows how to add them. That's what a quantum repeater is. A disciplined refusal to let loss and chance dictate your reach. And when an end-to-end entangled pair finally appears between cities that never saw the same photon, you feel the rare calm that comes from a promise kept by many hands. Memories that waited without drifting, heralds that spoke only when they had reason, and swaps that respected what could and could not be known. So that distance for once was not a barrier but a rhythm. Photonic cluster states for one-way computing. You're handed a tangle of light that, at first glance, looks like wasted effort. Photons linked in advance into a sprawling web. And someone tells you that if you only measure them in the right order, with tiny nudges to your settings as you go, a computation will unfold without a single gate fired on demand. That is the quiet shock of photonic cluster states for one-way computing. You build the difficulty up front by preparing a highly entangled resource, then you spend it by measuring one photon at a time, letting each outcome steer the basis of the next. And in that gentle cascade, the algorithm appears as if you were carving a statue by removing pieces rather than assembling parts. To feel how this can possibly work without dense math, picture each photon as a node in a graph, and each entangling link as a thread between nodes. The entire web, called a cluster, encodes a reservoir of computational potential, and your only tool afterward is measurement. Choose a basis for the first node, and you effectively apply a small, controllable quantum gate to the logical information that lives in the web. Then that photon is gone, and the information has hopped to its neighbors in a slightly transformed form. Keep going with a sequence of adaptive measurements. Adaptive because each choice may depend on earlier outcomes, and by the time you've trimmed away a swath of nodes, the remaining unmeasured part of the web holds the answer you designed it to yield. The surprise is not that measurements matter. The surprise is that only measurements are enough once the web is woven, and that the real-time corrections you would normally implement as physical operations can be replaced by a bookkeeping trick called frame tracking. You reinterpret future measurements in shifted bases, rather than forcing the light to pass through corrective elements, which keeps the table quiet and the pace brisk. The entire enterprise hinges on making the right kind of web and doing so fast enough that losses don't shred it before you meaningfully begin. In the photonic world, the building blocks are sources that spit out single photons on cue and optical gadgets that fuse them into entangled pairs and larger graphs. Early labs relied on nonlinear crystals that produce pairs at random, and then stitched those pairs together with beam splitters and detectors that heralded success. A process that feels like trying to knit a sweater while half your stitches vanish. So the community learned two strategies to tame chance. First, multiplexing, where many sources and many paths work in parallel and fast switches, route only successful pieces into the main tapestry. Second, time bin architectures, where a single or few sources create a long train of photons, and loop-based circuits entangle successive time slices so the cluster is stretched along the clock rather than spread across costly hardware. As sources matured, quantum dots in tiny cavities that emit near-identical photons with clockwork timing, and integrated waveguides that perform low-loss routing, the ability to grow long chains and two-dimensional patches improved. And those patches are crucial because one-dimensional webs can only transport and rotate information, whereas two-dimensional and higher clusters can enact the full palette of logic. If you need a mental picture of a fusion without algebra, imagine two small entangled pairs carried on separate rails. You briefly overlap one rail from each pair on a beam splitter and watch the joint pattern of clicks. A particular coincidence announces that the pairs have merged into a single, larger entangled piece, in which the two untouched photons become neighbors in the new graph. Repeat this many times with care and redundancy, and a carpet of connectivity emerges, big enough to host meaningful algorithms. For large-scale machines, this carpet must be fault-tolerant, which sounds forbidding, but comes down to an old idea used in a new way. You embed your logical qubits in a robust pattern within the cluster, often a three-dimensional structure whose extra dimension is not physical space but the progression of measurements in time, and you arrange your measurement bases so that errors reveal themselves as local, readable changes in certain parity checks. You then decode those changes to infer and correct what happened without ever touching the photons that have already flown by. Designs inspired by topological codes use this approach to set explicit thresholds. Keep loss and noise below a few % per operation, maintain enough connectivity, and your one-way computer can in principle run as long as you like. Exceed those limits and the web frays faster than you can mend it. There is a sister branch that trades single photons for continuous variables. Bright beams of squeezed light combined on beam splitters to make cluster states whose nodes are modes rather than particles. There, homodyne detectors measure quadratures instead of discrete clicks, and classical feed-forward adjusts small phase shifters in real time. While these Gaussian resources alone cannot implement every gate, modest injections of non-Gaussian elements, single photon additions, special measurements unlock universality, and the advantage is that integrated optics can produce and handle very large clusters at radio-like speeds using mature components. No matter the flavor, the bottlenecks are honest and teach you where the craft lies. Indistinguishability of photons, so interference is clean. Detection that is both efficient and fast so you can keep pace with the flow of outcomes. Switches that redirect light without adding glare. And calibration that holds phases to within a whisper over thousands or millions of trials. The control software, too, is part of the machine. It must take a flood of detector outcomes, update the abstract frame that tracks pending corrections, and set the next measurement angles, all within nanoseconds to microseconds depending on your architecture. There is no room for hesitation because the photons are already on their way. If you wonder why go to all this trouble when there are other quantum platforms, the answer is that light is the natural courier. It moves at speed, couples weakly to its environment, and travels through fibers and free space with grace. A computer that thinks by consuming a pre-wound fabric of light can, in principle, scale through temporal multiplexing rather than sheer component count, growing depth by running longer and width by operating more modes in the same footprint. Moreover, the very same hardware can double as a network node, prepared to send intermediate states to distant processors or accept fresh cluster pieces via fiber, knitting distributed computation from separate labs. Yet none of this relies on romance. Real demonstrations today already show kilometer-long cluster chains created by a single source and a loop, multi-photon patches stitched on chips with integrated beam splitters and phase shifters, and small algorithms, state teleportations, logic primitives, sampling tasks, executed by measuring and adapting rather than by shuttling photons through cascades of fragile gates. The road to large general-purpose machines is paved with pragmatic milestones, pushing source brightness without sacrificing purity, lowering loss in on-chip switches, stabilizing phase over hours so adaptive choices stay meaningful, and embedding full error decoding in control electronics so the user sees a stable programming model rather than a frantic optical ballet. If you keep a softer lens on the story, there's a lesson that reaches beyond photonics. Sometimes the most reliable way to act is to invest in structure first and then let small, local choices reveal the global result. One-way computing is that philosophy turned into light. You prepare a connected possibility, then trim it with care until the shape you need emerges. No brute forcing, no frantic corrections, just a measured conversation between preparation and observation that leaves you, at the end, with answers carved from a web that quietly disappears as it does its work. Boson sampling, quantum advantage by interference. You're invited to watch a machine that doesn't solve a tidy puzzle so much as let nature perform one for you. A maze of glassy paths and beam splitters where you release many identical, single photons at once, then simply count which output ports click. And the claim, which sounds bold until you sit with it, is that those counts form patterns that ordinary computers can't reproduce in any reasonable time because the underlying bookkeeping is not multiplication or addition but a brutally hard combinatorial tally of all the ways bosons can flow together. This is boson sampling, a demonstration of quantum advantage by interference rather than by long gate sequences. And to understand why it matters, you only need a few solid pieces. Indistinguishable photons prefer to arrive together in certain outputs and avoid others. Linear optics mixes paths without adding noise of its own, and the probability of a particular set of detectors clicking is governed by a summary of the interferometer's submetrics that mathematicians call a permanent, easy to define, punishing to compute at scale. So when you let the experiment run and gather many samples, you are effectively drawing from a distribution whose exact shape is thought to be out of reach for classical algorithms once the device gets large enough and clean enough. In practice, the device looks disarmingly simple: an array of sources clocked to emit single photons on demand, an integrated photonic chip whose waveguides, splitters, and phase shifters scramble the paths in a way you can calibrate but not invert with tricks, and a bank of fast, low-noise detectors that report where each photon landed. Yet everything hangs on three uncompromising details. Your photons must be near twins in color, timing, and spatial mode so that they truly behave as bosons that can interfere. Your circuit must be deep enough and irregular enough that many path combinations contribute with different phases, and your losses must be low and well characterized, because every missing photon quietly reshapes the distribution you think you're sampling. Early experiments used probabilistic sources that spit out pairs and kept one photon as a herald while sending the other into the chip, a method called scattershot that boosts the rate by accepting any subset of sources that happen to fire. More recent machines favor brighter, cleaner emitters and clever multiplexing so that many time bins or spatial channels are available, and a controller routes successful emissions into the computation while discarding the rest. In parallel, Gaussian boson sampling replaces single photon sources with squeezed light, making a different but related distribution whose probabilities are linked to another hard object. And that variant has sparked proposals for concrete tasks like finding clusters in graphs or modeling certain molecular spectra, offering a hint that sampling might one day do more than challenge supercomputers for sport. If you wonder how anyone can tell the device is doing something classically intractable rather than producing junk, the answer is layered rather than glitzy. You start small and verify against exact calculations. You scale and use statistical tests that distinguish your data from easy imposters like uniform noise or fully distinguishable photons. You exploit suppression laws for special circuits, where symmetries make some outcomes essentially forbidden, if indistinguishability holds. You compare the frequencies of heavy versus light outputs according to simple predictors derived from the interferometer, and you run likelihood ratios against tractable approximate models to show your samples are too structured to be fakes, yet too complex to be simulated exactly at your size. Alongside optimism lives candor. Algorithmic advances on the classical side keep raising the bar by simulating larger devices than anyone expected a decade ago, especially when the quantum hardware has realistic flaws like partial distinguishability, mode mismatch, multi-photon contamination, and detector dark counts. The back and forth is healthy, because a fair claim of advantage must survive not only today's simulation techniques, but the next batch too. Practical teams therefore publish not just a headline size but full calibration, source purity and brightness, measured overlaps between photons, circuit loss maps, detector characteristics, and they stress test their own claims by feeding those imperfections into the best available classical codes to see whether the gap remains. The craft of making the interference honest is equal parts optics and patience. You stabilize temperatures so path lengths don't drift. You lock phases and equalize arrival times with sub-picosecond care. You filter spectral tails so photons share a clean bandwidth. You flatten source power to avoid unwanted two-photon events. You deploy cryogenic superconducting detectors that count with high efficiency and low false clicks. You design chips with low propagation loss and with tunable elements that let you sample many effective circuits without fabricating a new one each time. And you build control software that can reconfigure, collect, and analyze at scale without smuggling in assumptions that favor your desired conclusion. Philosophically, Boson sampling is a strange sort of computer. It does not output a neat number or a certificate you can check in a second. It outputs a stream whose statistics carry meaning, and you learn by comparing, not by reading a single line. Yet, that very strangeness reflects an honest view of complex problems. Many of the hardest questions we care about are themselves about distributions rather than single answers. And a tool that samples from a landscape beyond classical reach may open doors even if you cannot label each step with a tidy proof. It's equally important to temper hype. Boson sampling is not a universal quantum computer. It does not run arbitrary programs, and by itself, it does not solve the encryption challenges that fill headlines. Its value today lies in being a clean, demanding benchmark that pushes source technology, integrated optics, and detection toward regimes useful for more programmable photonic processors, and in exploring whether specific sampling tasks can be harnessed for niche but real benefits. Screening large graphs for structure, generating seeds for combinatorial searches, assisting certain spectroscopy analyses, where even modest quantum edges translate into saved time or energy. The deeper lesson you carry out of the lab is about leverage. When the rules of combination are right, complexity accumulates in your favor, not as noise, but as structure, and the uncountable ways bosons can co-occupy paths become a resource rather than a curse. You don't force a solution with heavy machinery. You prepare conditions under which tiny, indistinguishable pieces arrange themselves into patterns a classical tally cannot follow. Then you listen long enough for those patterns to become undeniable. In that sense, Boson sampling is a method as much as a milestone, a reminder that advantage sometimes arrives not by building taller stacks of logic, but by stepping aside and letting interference do the bookwork you would never finish by hand. Random circuit sampling on superconducting chips. You don't prove a new engine by hauling a useful load the first day. You run it hot, on a track you designed to expose its weak joints, and you listen to the rhythm until the rattles fade. Random circuit sampling on superconducting chips is exactly that kind of trial. A stress test where you program a grid of transmon qubits with a deep sequence of pseudo-random 1 and 2 qubit gates. Ask the device to spit out bit strings according to the quantum rules it just enacted, and then check whether those strings look like they came from the intended chaotic circuit, rather than from a tired classical guess. The chips are slabs of aluminum or niobium, patterned into tiny nonlinear oscillators that behave as qubits below a few tens of millikelvin inside a dilution refrigerator. Each qubit tied to a readout resonator and to a handful of neighbors through tunable couplers. And the randomness is not a shrug, but a recipe. layers of single-qubit rotations that point block vectors in new directions, sprinkled with entangling operations like controlled phase, or eye-swap on a tiling that marches across the chip so correlations percolate outward, cycle after cycle, until the overall transformation reaches the messy, anti-concentrated regime where small errors grow visible and classical shortcuts lose footing. Running such a test turns out to be more about discipline than bravado. You first tame each qubit's personality with calibration routines, so a drive pulse rotates by the angle you think it does. Pulse shaping like drag helps avoid leakage to unwanted levels. You tune couplers so 2-qubit gates hit their marks without splashing phase onto bystanders. And you map out which frequencies play nicely together so the crowd doesn't talk over itself. Only then do you press start on circuits whose gate lists were chosen by a computer, but whose success rests on your lab craft. Quiet cables and attenuators that keep thermal noise out. Cryogenic amplifiers that boost readout signals without drowning them in hiss. Filters that keep pump tones from seeping into places they don't belong. And shielding that keeps wandering magnetic fields from tugging qubits off key. When the run begins, each trial lasts microseconds. Qubits are initialized, the random gate stack is executed, the state is measured in the computational basis, and a 90-something bit string pops out. Repeat 1,000,000 times, shuffle the circuit settings, and you own a mountain of data that, if your device behaved, will show a particular signature called Porter-Thomas-like weighting. Most outputs are rare, a few are surprisingly heavy, and the heaviest outputs track where the true quantum amplitudes were largest for that specific random instance. Because no one can exactly compute the full distribution for the largest experiments, validation leans on checks that scale. On smaller subcircuits, you compute the ideal probabilities and compare with the observed frequencies to estimate a fidelity number. On larger instances, you use cross-entropy benchmarks that score how much your outputs seem biased toward the ideal heavy hitters compared with uniform noise, or with data generated by deliberately dephased models. You also flip to mirror circuits, run a random block and then its inverse, where a perfect device would always return the all zeros bit string, a blunt test that the gates and their calibrations hang together over depth. And all along, you track assignment fidelities of measurements, crosstalk between lines, and drifts in qubit frequencies so that you can attribute a sagging score to a cause you can fix rather than to bad luck. The honest tension in these demonstrations is the race with classical simulation. As hardware scales, theorists sharpen algorithms that contract the circuit tensor network more cleverly, split the computation across clusters, or exploit the specific layout of your chip to prune the search. That's not a reason to retreat. It's the point of a benchmark that it provokes both sides to improve. So credible claims report the full context. Number of qubits and cycles, gate set and layout, measured 2-qubit and readout errors, estimated fidelity from cross-entropy, and a transparent accounting of how much energy and time a state-of-the-art classical simulator would need for the same instance given those imperfections. What makes random circuits especially revealing is that errors don't hide. Coherent miscalibrations echo as patterns in the output statistics. Leakage out of the computational subspace spoils mirror tests in a telltale way. Correlated noise shows up when simultaneous randomized benchmarking degrades more than the sum of its parts. And crosstalk sneaks into parity correlations you didn't ask for. To fight back, teams use randomized compiling to scramble coherent errors into stochastic ones that average out more benignly. Interleave calibration shots with data shots to track drift in real time, and design layer patterns that spread entangling gates across the chip to equalize wear. It might sound like a contrived contest. Why sample a distribution with no direct practical use? But the payoffs are concrete. The same gate quality and calibration stability that lift random circuit scores also lift the prospects of error-correcting codes, where long sequences must run without wandering phases. The same readout improvements that separate heavy output distributions cleanly also shorten the time needed to extract stabilizer syndromes. And the same control software that adapts to millions of random gate lists becomes the backbone for compilers that will one day schedule real algorithms with equally demanding depth and connectivity. There's also a quiet education in how confidence is earned. A A flashy single run means little. What convinces is a ladder of experiments, small, then medium, then large, each with checks calibrated to its size, each reproducible on different days, and each robust against tweaks intended to expose shortcuts. It's telling that the community has learned to publish not just raw advantage headlines, but error budgets, redundancy in tests, and side-by-side comparisons with the latest classical methods, because the bar for belief should rise with the claim. The near future of these chips folds random sampling back into day-to-day development. Use it to map spatial variations in noise across the die, which couplers drag you down. To test new fabrication stacks that promise longer coherence. To stress multi-chip modules where signals cross interposers. And to quantify whether pulse-level optimizations that look good in isolation still look good when thousands of gates jostle in tight quarters. As logical qubits arrive, a version of the same idea, randomized circuits at the logical level, will serve as a yardstick for whether error correction is buying real depth, not just headlines. If there's a gentler lesson in watching a refrigerator-sized machine spray out bit strings for hours, it's this. Sometimes the honest way to gauge a system's readiness is not to hand it a carefully curated task. It can be coached to ace, but to send it into a maze it cannot memorize and see whether its nature, coherence, connectivity, control, wins on its own. Random circuit sampling is that maze for superconducting chips, a steady, humbling way to surface flaws, reward quiet engineering, and, when the data finally tilt decisively toward the ideal distribution, feel a kind of earned calm. Not that quantum has beaten classical forever, but that your particular machine is genuinely computing in a way no shortcut can cheaply fake today. And that this, more than a headline, is the kind of progress that sustains the long road to useful quantum algorithms. Noise tailoring, dynamical decoupling in action. You don't tame a noisy world by shouting over it. You learn its rhythm and step between the beats. And that is the spirit of dynamical decoupling, a quiet choreography of control pulses that makes a qubit forget the slow, clumsy hands of its environment while staying alert to the motions you actually care about. The basic move is humble enough to teach in a minute. Let a qubit precess for a while, so any tiny frequency error or wandering field nudges its phase. Flip it halfway through with a sharp pulse, and the second half unwinds the first like walking back along your footprints. So at the end, the net phase error is near zero, even though the noise never left. The classic spin echo. Stack that idea into a sequence, regularly spaced flips in the Carr-Purcell Myboom-Gill family, crisscrossing axes in XY4 and XY8, non-uniform timings in Uhrig's prescription, and you discover that each pattern acts like a handmade filter that suppresses certain fluctuation speeds while letting others through, which means you can tailor your qubit's hearing, hush the slow drifts that ruin memory, ignore the mid-band rumble during logic, or even amplify a narrow tone when the qubit is being used as a sensor. The reason this works without equations is that noise isn't one thing. It's a spectrum, a mix of glacial drifts from thermal wander and power supplies, gentle waves from mechanical vibrations and magnetic hums, and quick jitters from electronics. And your pulse train carves notches and passbands into that spectrum as far as the qubit is concerned. Evenly spaced flips cancel the leisurely stuff, but can accidentally resonate with periodic trouble. So you rotate the axes to average away pulse imperfections, and you stagger the timing to shove the filter's blind spots exactly where the lab's nastiest frequencies live. In that sense, dynamical decoupling is less a single technique than a family of listening profiles you load into the device. On superconducting chips, those profiles let quantum states nap for milliseconds instead of microseconds by silencing slow flux drift and charge wander. In trapped ions, they keep magnetic noise from smearing delicate phase relationships while multi-qubit gates run nearby. In semiconductor spins and color centers in diamond, they turn fragile defects into honest quantum memories that hold entanglement while photons are routed or while distant partners catch up. And in nanoscale magnetometers, they are used upside down as bandpass recipes to make the spin deaf to static fields but hypersensitive to an oscillating field at a chosen frequency, so weak signals from a single molecule, a tiny current loop, or a faint radio tone can stand above the ambient murmur. Once you see pulses as filters, you also see how to probe the noise itself. Vary the spacing and count how quickly coherence decays. Then invert that record to reconstruct the noise spectrum your qubit experienced. With that map in hand, you place the sequence's notches where the spectrum peaks, tighten the schedule where drifts grow, or redesign the control electronics that produce the worst of it. The lesson is practical and empowering. Don't beg for a quieter world. Measure it and sculpt your defenses. But the dance has limits you must respect. Real pulses take time and have errors, so piling on flips eventually backfires by injecting mistakes faster than they erase noise. To push that boundary, you use composite pulses that self-correct, alternate axes to cancel systematic over or under rotations, and sprinkle randomness over the sequence, so any leftover coherent errors scramble into harmless diffusion instead of building a steady bias. Qubits also have to do work, and naively slamming echo sequences during logic would erase the very phases your algorithm needs. So modern schedules interleave decoupling with gates or fold noise suppression into the gate design itself. Dressed gates that include tiny pre- and post-rotations, echoed cross-resonance, and other tricks that let computation proceed while the environment is being politely ignored. There's a deeper compatibility issue that engineers have learned to finesse. The best decoupling sequences assume you can flip fast compared to the noise you want to cancel. But control lines and resonators have bandwidth limits, and flipping too hard can wring the hardware or spray energy into neighbors. So tailoring often means balancing 3 dials at once: pulse speed and shape, qubit spacing and frequency to avoid crosstalk, and the specific axes used to keep nearby operations undisturbed. When this balance is struck, the payoffs show up everywhere you care to look. Memory qubits hold states long enough for network messages to arrive. Stabilizer measurements in error. Correcting codes become more repeatable because low-frequency drift is muted between rounds, and calibration routines last longer before needing refresh, making an entire processor feel calmer and more predictable. Even at the level of a single experiment, the method teaches caution and creativity. If your coherence time improves under a standard echo but refuses to budge under more elaborate trains, the culprit is probably fast noise you can't outrun with flips and must fix at the source. If a sequence that worked last month now shortens coherence, a new periodic interference has crept in and is being amplified by your chosen timing. And if flipping a qubit during sensing kills your signal, you have accidentally notched out the very frequency you hoped to detect. Time to retune the spacing so the target sits in the passband while the background sits in the trough. Some of the most elegant uses are in systems that must keep entanglement alive across distance. Apply synchronized decoupling to both halves of a pair, and the shared phase survives even if each lab's local fields drift independently. Apply carefully mismatched sequences, and you can deliberately imprint a controlled phase for metrology without opening the door to common mode noise. And in hybrid devices, spins coupled to mechanical motion or to microwaves, it is now routine to tailor sequences that protect one interaction while averaging away another. So coupling becomes a dial rather than a property you endure. As hardware matures, decoupling merges with higher-level error handling. Randomized compiling turns slowly varying control errors into stochastic noise that error-correcting codes can catch more efficiently. Spectator qubits that aren't part of a given gate cycle receive background echoing so they don't drift while they wait. And pulse schedules are chosen by software that ingests live noise spectra and spits out sequence parameters in real time, closing the loop from measurement to mitigation without a human in the middle. It's worth being honest about what dynamical decoupling does not do. It cannot cancel energy relaxation, which comes from real jumps rather than slow drifts, and it cannot rescue a system dominated by high-frequency chaos. It is also no substitute for good materials, clean wiring, and quiet power. Treat it as a scalpel, not a broom, but inside the wide space where many quantum platforms actually live, where slow wander is the bully and specific mains hums and mechanical tones decorate the background, decoupling is the cheapest, most portable way to buy coherence, sometimes by orders of magnitude, with nothing more exotic than timing and phase. If you're looking for a human-sized lesson to take away when the Pulse programmer's window closes, it's this. You don't always fix noise by fighting harder. You fix it by listening first, by shaping your actions so error accumulates where it cannot hurt and cancels where it can. Dynamical decoupling is that mindset turned into a schedule. Choose your moments, flip at the right times. Let the second half of the day undo the first. And the reward is the calm, reliable memory that every quantum device craves. Not because the world got quieter, but because you finally learned its beat. Error detection with surface codes. You begin with a square of quiet hardware that looks almost boring. Rows of qubits sitting 2 by 2 under a web of lines. And then someone explains that the calm hides a plan. You won't try to keep a single fragile qubit perfect. You'll spread one logical bit of quantum information across many, and listen for small inconsistencies that betray where the world has tugged. That is error detection with surface codes. And it works because you trade the impossible task of watching an invisible state for the practical task of watching relationships, parities, among neighbors, that your circuit can check again and again without disturbing the computation itself. In a surface code, most qubits carry data only indirectly, and a second set, the measurement qubits, serve as local referees. Each referee asks the same limited question every round. Do the states of my nearby data qubits agree in this specific way? And returns a single yes or no. By itself, one answer means little. But when you repeat the questions rhythmically and lay the answers out across space and time, patterns pop out. Isolated flips, short chains, or extended streaks that sketch where errors must have wandered. You never measure the logical state head-on. You measure these small checks, called stabilizers, and infer the rest. That is the first lesson. Preserve what matters by monitoring constraints rather than prodding the thing you want to keep. The lattice has 2 flavors of check, one that is sensitive to bit-type mistakes and one that is sensitive to phase-type mistakes, and the borders of your patch are chosen so that a chain of errors must cross many links to impersonate a logical flip. The longer that minimum chain, the larger the distance of the code, and the better your odds that local noise cannot fake a global change. Because measurements themselves are noisy, you do not trust a single round. You stack rounds into a history and decode in space-time, treating a suspicious answer that appears only once as likely measurement error and a trail of consistent answers as evidence of a real change on a data qubit. In practice, a classical algorithm gathers the detection events, the moments when a check flips from its usual answer, and pairs them up like footprints after a snow, choosing the simplest set of error paths that could explain what you saw. That decoder can be a fast-matching routine, a message-passing scheme, or a learned model tuned to your device's habits. But its job is always the same. Translate a field of small local alarms into a calm, global decision about whether a logical correction is needed, and update the Pauli frame, the software ledger that says how to interpret all future measurements so you don't waste precious time physically undoing every bump. The surface code's realism shows in its circuits. Each round is a little dance. Entangle a referee with its neighbors through a short sequence of gates arranged so that single faults cannot spray damage too widely. Measure the referee quickly, reset it, and move on. Care is taken to avoid hooks, where a control mistake during this dance could stretch into a 2 data qubit error and mimic a logical fault at smaller weight than promised. Careful ordering, occasional extra flags, and using different axes in different rounds tame these hooks, so your distance really buys what it claims. The code is geometric for a reason. Local checks mean local wiring and local wiring scales. You can tile patches across a chip, assign some to hold data and others to perform operations, and then do logic not by dragging qubits through long gate sequences but by lattice surgery, merging 2 patches to learn a joint parity and then splitting them again so that information has been woven together without moving the physical carriers. Twists and boundaries implement different logical axes, and braiding defects or toggling who is merged with whom realizes the building blocks of computation, while the background rhythm of detection never stops. Threshold is the next grown-up idea you meet. Below a certain physical error rate per gate and per measurement, adding qubits to increase distance drives the logical error down exponentially. Above it, more qubits only make things worse. That sharp dividing line is not a slogan, but a design target that turns vague noise budgets into actionable engineering. Hit the threshold with your 2-qubit gates. Readout and crosstalk and scaling starts to work in your favor. Real chips earn this by handling nuisances the textbooks soften. Leakage into unwanted energy levels can masquerade as odd patterns of checks, so you insert tailored resets and swaps to pull strays back into place before they cause correlated faults. Bias in the noise. Bit flips more common than phase flips, or the reverse, can be turned from a liability into a design choice by picking check layouts like the so-called X variant that shoulder more of the dominant error type and give you a better threshold for the noise you actually have. Correlated drift across rows can be spotted because it leaves long, low-frequency scars in the detection map. And you answer with decoders that know about time correlations, rather than treating every round as independent. Verification here is never a single plot. You run many patches at many distances. You vary the number of rounds before you read out, and you check that the rate at which logical errors slip through shrinks with distance in the way theory predicts. You also stress the system with intentional faults, inject a known pattern of gates that should flip certain checks, and confirm that your alarms ring precisely where expected. When the curves bend the right way across weeks rather than days, you know you have not merely tuned around a good afternoon, but built a process that holds. The most sobering part is how much of error detection is really about rhythm. The code works only if you keep the metronome steady. Gates that land on time, measurements that complete, resets that clean house, because irregular timing turns manageable noise into surprises the decoder wasn't trained to expect. So you build control stacks that are as much about determinism as about speed. You reserve bandwidth for syndrome readout even when user gates are quiet. And you design the system so background checks keep running while higher level software thinks. And then there is the honest limit. Surface codes detect and correct the gentle, local lies the world tells, but they do not fix energy loss outright, and they do not rescue computations that allow wide, fast crosstalk to paint identical errors across many sites at once. That is why shielding, materials, and clean microwave control are not optional frills, but the foundation on which the code rests. Yet when the foundations hold, the experience is quietly transformative. Strings of detection events thin out as distance goes up. Parity histories become predictable, and the logical qubits feel less like nervous cats and more like well-tended clocks. You discover that reliability at scale is not an accident of one heroic component, but a community effect. Neighbors watching neighbors, small questions asked relentlessly, and a decoder that converts many tiny truths into one steady correction. If you carry one human-sized lesson from this lattice, let it be this: you protect delicate things by surrounding them with structure, by defining local promises you can keep, and by honoring a cadence that never misses a beat. And in that structure you earn the right to compute longer than any single element deserves. Not by denying noise, but by noticing it in time to guide it harmlessly to the edge and let the work continue. Anyon signatures in engineered materials. On a wafer no bigger than your palm, you can stage a drama that ordinary particles don't know how to play. And the first surprise is that you don't see it by looking harder, but by listening differently. You cool a two-dimensional electron gas until motion quiets. You turn on a strong magnetic field so orbits curl into tidy lanes. And then you ask the system questions that only anyone's can answer. Questions about fractional charge, about phase that remembers who encircled whom, about heat that marches along edges in quantized steps. And as you collect the replies, a new kind of matter steps forward from engineered materials that were, a moment ago, only semiconductor sandwiches and patterned metal gates. You start with the gentlest probe. Let current trickle through a narrow constriction, a quantum point contact, where edge channels from opposite sides of a fractional quantum Hall fluid nearly touch. Each tunneling event is the hop of a quasi-particle, and the granular hiss of those hops, measured as shot noise, tells you the size of the carriers one by one. When the noise implies charges like 1/3 or 1/5 of the electron, you have your first signature that the fluid's excitations are not electrons at all, but collective ripples with fractional charge. a fact that isn't decoration but a doorway to their statistics. Charge is only half the story. Statistics is the other, and you read it with interference. You carve a tiny interferometer in the edge, Fabry-Perot like a small arena, or Mach-Zehnder like a racetrack, and you let quasi-particles choose between two paths around a central island. The oscillations in conductance as you vary magnetic field or gate area carry two phases intertwined, the familiar Aharonov-Bohm phase and the stranger statistical phase that appears because, in 2 dimensions, trading places is not a shrug, but an operation with a memory. When the number of trapped quasi-particles in the island changes by 1, the oscillation can slip by a fraction of a period, a fingerprint that the passerby picked up a phase only available to anyone's. Getting this right in the lab is fussy. Coulomb charging can overpower clean interference, and edge reconstruction can split the current into multiple filaments. So you tune to regimes where area is stiff, screening is controlled, and temperature is low enough that coherence survives the loop. And only then do the phase steps settle into a rhythm you can trust. You don't rely on a single melody, you move to tunneling exponents next, because edges of these fluids behave like one-way, interacting strings, where the current voltage curve bends with a power that encodes the edge's internal grammar. Log-log plots that refuse the straight line of a Fermi liquid tell you that your edge is a chiral Luttinger liquid, with exponents predicted by the underlying topological order. As you change filling factor confinement, or the strength of the point contact, those exponents shift in specific testable ways, adding another layer to the case that you are not watching ordinary carriers jostle through an ordinary wire. Heat joins the conversation when charge is too coy. A hall bar with heaters and thermometers on the edge can measure thermal Hall conductance, the rate at which entropy slides along a boundary. In certain states, the conductance comes in discrete universal quanta, tied to the number and chirality of edge modes, and, strikingly, to the presence of neutral modes that carry energy but not charge. When your measured heat flow lands in the right multiples, it certifies the edge content predicted by the theory of that topological phase. If it shows a half-quantized step where no simple integer lives, it whispers of more exotic, possibly non-abelian order that saves its sharpest signatures for braiding experiments but leaves thermal breadcrumbs you can follow today. Yet you stay humble. Thermal measurements are exquisite balances of small signals against parasitic leaks, and careful null tests, reversing field, swapping contacts, mapping backgrounds are how you keep wishful thinking out of the headline. Not all engineered anyones live in high-mobility GAAs. You can grow them in graphene, where relativistic band structure and cleaner substrates open windows to fragile fractional states at higher temperatures and in stronger fields. You can coax them into moiré materials where flat churn bands mimic Landau levels without magnets, and where fractionally filled bands may host quantum anomalous Hall cousins of the classic fluids. And you can search for their cousins in candidate spin liquids, magnets on frustrated lattices that never freeze into order, but instead harbor excitations, spin-ons and visons, that behave like anyone's. There, the signatures are subtler. A continuum in neutron scattering where sharp magnons would be, a thermal Hall effect without mobile charges, and low-temperature specific heat that hints at deconfined fractional pieces rather than a tidy symmetry-broken ground state. Each clue is contestable on its own, but when transport, thermodynamics, and spectroscopy rhyme, the picture hardens, because anyone's are as much about braiding as about being. Device designers learn to choreograph motion. Gate-defined antidots can trap single quasi-particles whose number you can step one by one. Combining 2 constrictions lets you send a mobile anyone around a trapped one and watch the interference phase jump by the statistical angle. In proposals and first steps toward non-abelian tests, interferometers are tuned so that outcomes depend on the fusion channel of anyone's inside, producing visibility patterns that switch discretely when a hidden topological qubit flips. Making these experiments behave is a craft of temperature, sub-Kelvin so phase holds, cleanliness so that puddles don't introduce unwanted anyones, and time so that the trapped configuration is stable long enough to complete a braid. Along the edges, you learn to separate neutral modes from charged ones. Upstream energy flow that leaves charge measurements unchanged, but perturbs noise and dephasing can be the tell of an unconventional edge structure. By placing absorbers and thermometers at strategic spots, you can prove heat is moving against the current while charge glides with it. A paradox only topological edges resolve. You then fold those observations back into which effective theory, which K-matrix, which order, describes the bulk. Even the mistakes teach you. If your shot noise inferred charge drifts with temperature, you are in a regime where tunneling is dominated by agglomerates of anyones rather than the fundamental one. If interference fringes wash out as you press the point contact, you may have pushed into a Coulomb-dominated island where phase is set by charging, not area. If thermal conductance exceeds the predicted integer, unseen reconstruction has added modes you must model. Each detour is a map of the boundary between engineered theory and engineered reality. And walking that boundary honestly is the only way the signatures rise above rumor. Beyond electrons and spins, metamaterials let you emulate anyonic rules with light and sound, lattices of microwave resonators, patterned superconducting circuits, and photonic crystals can simulate the tight binding models whose excitations braid with non-trivial phases, while the anyons there are effective rather than fundamental. The interferometry and defect braiding you practice on those platforms sharpen the tools you bring back to condensed matter, and sometimes return with their own surprises, like robust edge transport in classical waves that mirrors the quantum case so well you can prototype devices before you etch them in semiconductors. Through all of it runs a simple discipline. You don't claim anyone's by a single exotic graph. You assemble a portfolio, fractional charge with the right temperature and bias dependence, interference with phase slips tied to enclosed quasi-particle number, tunneling exponents that obey Schirel-Luttinger scaling, thermal Hall plateaus that match edge counts, neutral mode flow that fits the proposed order, and you ask each measurement to agree with the others under the same knobs. When they do, the word signature stops feeling like a tease and starts feeling like an identification card. And there's a softer cadence underneath the metrology. Anyons are not weirdness for its own sake. They are bookkeeping made physical. They show you that when the rules of composition change, when exchanging two excitations is not an invisible shuffle but a remembered twist, the world can store information non-locally, protect it against local probes, and move it around by braiding rather than by flipping bits. That is why people care about these signatures at all, because they point to topological order that could one day host computations written in world lines rather than in gates. But even if you never build such a machine, learning to hear fractional charge in noise, to watch a phase shift because of who wrapped around whom, and to count heat quanta, walking along a boundary changes how you see materials, not as piles of atoms, but as stages where relationships between paths, between edges, between defects are the real actors. When you leave the lab late, the wafer's still cold, you carry a quiet respect for the fact that the strongest evidence rarely shouts. It accumulates, trace by trace on a spectrum analyzer, fringe by fringe in a conductance map, microkelvin by microkelvin in a thermal trace, until the only sensible story is that your engineered sheet of matter now hosts particles that are less and more than particles, that remember braids, and reveal themselves not to the impatient eye, but to the patient ear. Majorana zero modes in nanowires. You don't normally expect a wire the width of a virus to hide a new kind of particle at its tips. Yet that is the promise and the puzzle of Majorana zero modes in nanowires. By marrying a semiconductor that loves spin-orbit twists to a superconductor that lends its pair-binding calm, then leaning on a magnetic field just enough to reshape the spectrum, you invite a phase of matter where a single electronic state splits in two and parks its halves at opposite ends of the device, as if information decided to live non-locally to protect itself. The minimal story you can carry in your pocket goes like this. Start with an indium, arsenide or indium antimonide wire because their electrons feel a strong, sideways push when they move. That's the spin-orbit effect. Wrap part of the wire in a thin shell of aluminum so superconductivity seeps in and opens an energy gap, and then tilt a magnetic field along the wire to compete with pairing. If the chemical potential is tuned near the lowest subband and the Zeeman energy passes a threshold, the effective one-dimensional system becomes topological, which in plain language means the wire's interior refuses to host. low-energy states, while each end insists on holding a special one at exactly 0 energy. The two Majoranas that together would form an ordinary fermion if you force them to meet. But that remains separate so long as the topological gap protects them. What you measure is never the Majorana itself. It carries no charge and no spin to grab. So experiments eavesdrop through a normal metal lead at one end, nudging with a tiny voltage and listening to current. In the ideal limit, a Majorana acts as a perfect Andreev mirror at 0 bias, converting electrons into holes with certainty and yielding a quantized conductance peak of pinned at 0 volts. In real devices, temperature, tunnel barrier strength, and dissipation blur this signature. So people learn to press beyond a single bright dot on a graph and ask whether the peak is robust across magnetic field and gate settings, whether it sits on top of a hard gap, a clean stretch of suppressed conductance that proves the superconductor isn't leaking spurious states, and whether it appears coherently at both ends when the wire is long. That last test matters because clever imposters exist. Ordinary Andreev-bound states trapped by smooth potential inhomogeneities can also mimic a 0 bias peak, especially near the wire's ends where soft confinement acts like a quantum dot. These quasi-Majoranas are local, fragile, and tend to shift about with tuning, while the genuine article is non-local and anchored by topology. So the field has moved from "did you see a peak?" to "did you prove it shares its identity across the device and survives being jostled?" Beyond tunneling, there are other fingerprints that fit the same quiet logic. In a short superconducting island, the parity, even or odd number of electrons, normally alternates the spacing of Blockade peaks. But in the topological regime, the two parities become nearly degenerate, and a 1μe periodicity emerges as if single electrons can pass through without paying the usual pairing toll. In Josephson junctions, a topological channel promises a periodic relation between current and phase, observable as missing Shapiro steps under RF drive. Though here, too, caution is essential because non-topological mechanisms can mimic the effect. And in deliberately designed T-junctions, braiding operations should imprint non-abelian memories on the joint state that no local probe can erase, a dream that motivates the architecture of more complex nanowire networks, even as the community is honest that unambiguous braiding has not yet been demonstrated. The material story underneath these signatures is its own education in what good means at the nanoscale. Early devices suffered a soft gap, a haze of subgap states that blurred everything, until epitaxial growth placed aluminum directly on the semiconductor to make atomically clean interfaces. That change hardened the gap and allowed the 0 bias features, when they appeared, to sit on quiet baselines rather than on noisy rubble. Electrostatic gates now carve tunnel barriers with fine control, adjust the chemical potential across different segments, and define islands and junctions without leaving the wire's protective shell too ragged. Magnetic fields are aligned with sub-degree care to avoid orbital vortex entry that would spoil coherence. And vector magnets plus local heaters stabilize the environment so that drift is slow enough for hours-long scans to mean what they say. As devices improved, theory kept pace and kept everyone honest. It showed how smooth potential variations can pin trivial states near 0 energy, how weak disorder erodes the topological gap and causes the two end modes to hybridize, splitting the 0 and producing oscillations with wire length and magnetic field, how dissipation in the leads can smear quantization and hide the physics under effective broadening, and how non-local probes, measuring conductance from both ends, correlating the motion of peaks, or injecting from one side and detecting at the other, can distinguish a single non-local fermion split in two from two unrelated local states. This back and forth is not a detour, but the way confidence is earned when the phenomena are subtle and the imposters are clever. If your interest is computation more than spectroscopy, the non-locality is not a curiosity, but the resource. Encoding a qubit in the parity of two far-apart Majoranas makes local noise less dangerous because no single, small disturbance at one end can flip the encoded bit by itself. Performing logic by braiding, exchanging the positions of Majoranas along a network of junctions, implements gates whose action depends only on topology. not on the precise timing of pulses. A graceful immunity that hardware engineers dream about. To get there, you need not only stable zero modes, but the ability to move them adiabatically without closing the gap, to read out parity quickly without heating the wire, and to couple islands in ways that enact controlled phase operations between logical qubits. Proposals abound. Measurement-only schemes that avoid literal motion by stitching outcomes. Fusion rule tests that check whether two Majoranas brought together behave like a fermion with a history. But the near-term milestones are more modest and more measurable. Long stretches of quantized zero-bias conductance that persist across gates and fields, end-to-end correlations that remain locked over hours, and gap spectroscopy that shows the bulk stays gapped while the ends host the only low-energy states in town. It helps to be clear about the limits. Majoranas will not fix loss, true T1-T1 processes, and they do not excuse sloppy fabrication. They require magnetic fields that can suppress superconductivity if the shell is too thin or riddled with defects. And they remain vulnerable to charged noise that moves the chemical potential, especially in short wires, where the two end modes can talk to each other. The path forward runs through longer, cleaner wires with uniform electrostatics, shells that survive higher in-plane fields, selective etching that defines junctions without ruining interfaces, and hybrid platforms that marry nanowires to high-quality, two-dimensional superconductors for better coherence and larger energy scales. Yet even before anyone draws a braid, the intellectual shift is already valuable. You learn to think of information as a global pattern rather than a local occupation, to treat zero energy not as an accident but as a protected feature of a phase, and to evaluate claims by portfolios of evidence rather than by single spectacular traces. When a device finally shows non-local zero modes that refuse to budge while every local nuisance is tuned and prodded, when the plateau holds its height as you thicken or thin the tunnel barrier, when the island's parity stops caring about length scales that used to matter, you feel a quiet click, the sense that you've coaxed a wire into hosting not a particle in the old sense, but a relation given physical form. And regardless of whether the first topological qubits you build from these relations ever run a grand algorithm, the discipline you practice to get there, clean interfaces, conservative interpretation, tests that look from both ends at once, will have taught you the same lesson the Majorana teaches the wire. That sometimes the safest place to store something fragile is in the space between its parts, where no single touch can undo it, and where, with patience, you can make certainty by design rather than by hope. Hybrid systems, light meets mechanics. You don't expect light to move anything you can feel, yet if you sit with a quiet cavity and a sliver of mirror thin as a hair, you learn that a few photons tapping in rhythm can tug a mechanical object enough for you to hear it with instruments. And that is the invitation of hybrid systems where light meets mechanics. You couple a vibrating thing, a membrane, a beam, a drum, even a levitated nanoparticle, to an optical or microwave resonator, and you let radiation pressure turn every tick of the field into a push, while every nanometer of motion turns into a shift of the field's color. That two-way conversion is the heart of cavity optomechanics, and once you see it plainly, you can do three families of work. Cool motion towards stillness, weave motion and light into coherent exchange, and translate information between worlds that would not otherwise speak. The cooling story begins with timing. You drive the cavity slightly red of its natural color so that a photon can only enter if it takes a quantum of vibrational energy with it. And each successful entry is a microscopic break on the mechanical mode, run in the resolved sideband regime, where the resonator's ring feels the individual teeth of the cavity line. Keep the environment cold and losses low, and the random jiggle falls until the motion's remaining blur is the zero-point twitch set by quantum mechanics itself. Labs verify they've truly reached that floor, not by wishful thinking, but by watching the asymmetry between light that steals a phonon and light that would add one. When the balance tips the way theory says, you've cooled honestly. Coherence follows cooling. If you detune and drive differently, a control beam can make the cavity and the mechanical mode hybridize into shared oscillations, where energy swaps back and forth faster than either leaks away. On a transmission trace, that exchange shows up as a narrow transparent window, optomechanically induced transparency, and in stronger coupling as a split pair of peaks. A clean sign that you're not just damping noise but steering dynamics. With short pulses, you can push this further, mapping the state of light onto motion and back in a controlled way. An optical write, followed by a read that brings the stored shape out again. So the resonator becomes a tiny, timed memory for field states or a way station in a routing protocol. Once you treat mechanics as a first-class quantum element, you can ask for more than cooling and swapping. You can create non-classical motion on purpose, for instance, by using a heralded scheme where a blue detuned pulse drives correlated creation of a photon and a phonon, and a partner pulse later converts the phonon back to light. Correlations between those outgoing photons betray that the mechanical mode carried a single quantum of motion in between. In other experiments, you feed in squeezed light to quiet the readout quadrature and watch the device produce ponderomotive squeezing, where the pressure fluctuations of the light are reshaped by the mechanics into noise that is lower than the vacuum level in one variable and higher in the conjugate one, a gentle but unmistakable signature that the field and the resonator shared quantum correlations rather than classical jostling. The platforms are diverse enough to feel like a catalogue of instruments. Photonic crystal nanobeams confine light and sound to the same tiny volume, so that a few photons reach strong cooperativity. Silicon nitride membranes, strung drum-tight, offer ultra-low internal loss and can be patterned to localize motion where light is strongest. Microtoroid and micro-ring resonators support whispering gallery modes that link optical waves to mechanical breathing via Brillouin forces. Piezoelectric films add a second doorway, coupling the same mechanical motion to microwaves through electric strain. So one mode can talk to both an optical fiber and a superconducting circuit. And in a different flavor, silica nanoparticles held in optical tweezers inside vacuum traps can be cooled by feedback until their center of mass motion is nearly in the ground state, creating free-flying test masses that respond to forces so weak you'd need a poet to name them. Each architecture comes with its own map of enemies. Clamping losses bleed phonons into supports. Two-level defects in amorphous materials soak up energy. Thermal photons in microwave lines sneak in if filters are sloppy. Alignment errors spoil overlap between optical and mechanical modes, and parasitic acoustic paths create dark ports that siphon coupling strength. The fixes are not magic. Better materials like high-stress silicon nitride or crystalline films, clean epitaxy at interfaces, phononic shields that reflect vibrational energy like mirrors reflect light, careful impedance matching in electrical lines, and honest cryogenics that cool the mechanical bath along with the resonator. But you feel their effect directly when the quality factors climb and the control beams can be dialed down without losing authority. The most ambitious role for these hybrids is translation. A mechanical resonator that grips a microwave circuit on one side and an optical cavity on the other can convert a fragile superconducting qubit's microwave photon into a telecom photon that rides fiber across a building or a city. To do this without drowning the signal. In noise, you synchronize the two couplings so that the mechanics serves as a quiet conveyor belt. You operate cold enough that thermal phonons are rare during the transit, and you temper stray modes, so the conversion bandwidth is useful rather than toy small. Experiments now report added noise below a handful of quanta and conversion efficiencies that climb steadily as internal losses shrink. And while the last few decibels are the hardest, the path is clear. Fewer spurious channels, stronger on-chip confinement of both light and sound, and integration that avoids lossy butt joints between separately made parts. Even when you don't care about networking, the same mechanics make sensors that are intellectually satisfying, because their calibration is written into physics rather than into the label on a box. The 0-point fluctuation of a cooled mode sets an absolute yardstick for displacement, and the shot noise of the light sets an absolute yardstick for readout. By shaping your control tones and feedback, you can choose whether the device rejects low-frequency drift, good for memory, passes a narrow band, good for detection, or purposefully converts a weak periodic force into a large phase shift on an outgoing beam. With that tuning, these systems detect mass loading at the level of a few molecules, map tiny forces from magnetic resonance near a single electron spin, and stabilize oscillators whose timing can anchor short baseline interferometers. Alongside the winds, you learn the guardrails. You cannot erase energy relaxation with clever, pulses. True damping is a sink. You must engineer away with materials, and if you push blue detuned gain too hard, the system becomes a parametric amplifier that screams rather than sings. Back action is not a story element, but a budget item. The same fluctuations that let light learn about motion push on the resonator and heat it. So you cancel or shape that push with two-tone drives that sculpt the noise spectrum, or you embrace it and use it to generate entanglement between two distant mechanical modes coupled to the same field. Either way, you count quanta honestly and publish the full accounting of added noise, bandwidth, and efficiency, so others can build on something firmer than metaphors. Verification here looks like good housekeeping rather than spectacle. You measure sideband asymmetry as a thermometer that doesn't need an external sensor. You perform ring-down experiments that reveal true mechanical dissipation without readout artifacts. You test that transparency windows shift exactly with drive power and detuning, and you swap in a known classical calibration tone to prove your amplifier chain doesn't invent sensitivity you don't have. When these checks agree for days rather than hours, you trust your conclusions enough to talk about quantum states of motion without flinching. The horizon is quietly exciting. Arrays of coupled mechanical resonators, patterned next to photonic waveguides, now act as programmable delay lines and mode converters for light while storing temporal patterns in sound. Microwave optical transducers with on-chip filters and impedance transformers are becoming compact boxes rather than science projects. Levitated platforms are approaching the regime where quantum control and macroscopic superposition tests overlap with precision sensing. And hybrid chips that combine mechanics with spins in diamond or rare earth ions promise memories that last long enough to buffer network hiccups without babying them at every step. And then there is the soft, human lesson you carry out of the lab after a night of aligning beams and listening to spectra. These systems reward gentleness and timing more than force. You get further by matching rhythms than by pushing harder, by learning the language of a tiny drum and humming along with light until the two keep time. In that discipline, there is a way of thinking that spills into everything else. You measure before you fix. You cool before you control. You trade single heroic leaps for sequences that let errors unwind. And you trust small repeated confirmations over single dramatic traces. When the cavity finally opens a narrow window that wasn't there before and the membrane's jitter falls beneath what you thought was possible, you don't feel magic, you feel relief. A reminder that even at the scale where photons count and motion comes in quanta, clarity can be built from patience, and that letting light and matter meet on their terms is sometimes the surest way to make them sing together.